are geometry of Banach spaces, vector measure, tensor product spaces, function algebras, approximation theory, etc. He is reviewer for Zentralblatt and Mathematical Reviews. He is also member of American Mathematical Society, European Mathematical Society, and also life member of Ramanujan Mathematical Society. Today he will be talking about orthogonality for biadjoints. I welcome both of you and I request Professor R.B. Bapat from ISI Delhi to chair this session. Over to you, sir.
Good morning, everybody, to this second day of the ICLAA. I'm very happy to host this session, and the first lecture will be a Hans Schneider ILS lecture by Steve Kirkland on disease inevitability on networks and opportunity for matrix theory. So I now request Steve to deliver his lecture. Over to Steve. Yeah, Steve. Yeah. Is there some problem? Steve, we cannot see your screen.
Can't hear us.
Yeah, we cannot hear, or the screen is coming in between, but again.
Sir, there is some technical issue while playing a while.
Greetings, everyone. Thanks very much for the invitation to speak at one of my favorite meetings, ICLAA. I'm going to tell you today a little bit about some joint work that I did recently with my friends and collaborators, Xixing Shuai, Pauline Brandon-Drisha, and Zuying. Greetings, everyone. Thanks very much for the invitation to speak at one of my favorite meetings, ICLAA. I'm going to tell you today a little bit about some joint work that I did recently with my friends and collaborators, Xixing Shuai, Pauline Brandon-Drisha, and Zuying Wang. And before I get going, I'll just say thanks to the International Linear Algebra Society that named this lecture as the Hans Snyder Lecture for this year. So I'm going to talk a little bit about something that's perhaps topical, outbreak of a disease. And the kind of thing I'm thinking about here is a disease outbreak that occurs heterogeneously in several different the talk is cholera. So that's a disease that's passed through contaminated water. And so, for example, you might have communities that are located at different sites. Is carried between the patches by the movement of the contaminated water. Another example, also topical, is something like SARS or COVID. So the patches are corresponding to cities, and the transportation routes that carry infectious individuals, say a network of airports, for example, admit the possibility that we can transmit the disease from one patch to another. Okay, so that's the context that I want to think about. And as I said before, it's heterogeneous. So each patch has its own particular characteristics for the disease, and there'll be things like the transmission rate from the pathogen to the host, or the pathogen decay rate, or the pathogen shedding rate. So that's like a reproductive rate for the pathogen, or the decay rate of infectious host individuals. So each disease, each patch has its own particular rates for the disease dynamics. And movement is made possible between the patches with parameters, I'll call them M sub ij, they're non-negative, and they represent the rate of the dispersal of the pathogen from patch J to patch I for each pair, I and J. Okay, so already we have a matrix lurking in the background there. And if there happen to be n patches altogether, then we can construct the corresponding movement matrix by just collating the MIJs into an n by n matrix, as well as the associated Laplacian matrix. And so I've written it as a formula there in terms of the movement matrix. So the idea is I make the Laplacian matrix by taking minus the movement matrix and then adding on a diagonal matrix consisting of the column sums of the movement matrix. And so that's what that formula represents there. So I'll just say, for those of you who like these kinds of things, this L is an example of an M matrix. So it's entry-wise non-positive off the diagonal, and it has 0 column sums. And so, of course, there's a weighted directed graph that's lurking in the background here, corresponding to the network of patches. And in the digraph, I have an arc from vertex J to vertex I, exactly in the situation that M sub ij is a strictly positive number. Okay, so what we want to do then, I'll just briefly outline the model for tracking the evolution of this epidemic spread. So for each patch, we keep track of the number of susceptible individuals, the number of infected individuals, and the number of recovered individuals, as well as the water. And as I said before, each of these has patch-dependent rates. And you model the entire thing as a system of coupled ordinary differential equations. Okay, so there's a disease-free equilibrium for that system in which every individual is disease-free, susceptible, and in addition, there's no pathogen in the water. That's the equilibrium point for that system of DEs. And then the question is, is the disease eventually going to become extinct inside of this patch network, or is it going to persist? That's an important question in trying to understand this model. Okay, the answer to that question is determined by what's called the network basic reproduction number, and the symbol for that is R naught. Okay, so if R naught is strictly less than 1, then the disease dies out, and if R naught is strictly bigger than 1, then the disease persists. And so I'm going to try and explain this R naught value a couple different ways. So for example, in terms of the system of differential equations, if R naught is strictly less than 1, then this disease-free equilibrium that we were talking about earlier is locally asymptotically stable. Okay, so that's good. And if R naught is strictly bigger than 1, that means that this disease-free equilibrium is unstable, bad. Another way of thinking about this R naught is as the expected number of infections that can be directly generated by a single infected individual. And so, of course, that's strictly, the R naught value is just strictly less than 1, you can see the disease dying out. If it's strictly bigger than 1, you can see the epidemic persisting. Okay, so the good news for us today is that this R naught value has a really precise meaning in terms of matrix theory. Okay, so what is it? Well, I've written it as a formula here. I've written rho of what I've got inside the brackets there is a matrix. I'll have D1 times D naught plus L all inverse times D2, where here's the notation. Rho denotes the spectral radius, and these D naught, D1, and D2, these are non-negative diagonal matrices, and they're capturing the information about the disease that is specific to the individual patches. Okay, so in other words, the kth diagonal entry in these diagonal matrices, they are, which matrix you're looking at, they are giving information about the transmission rate of patch K, the pathogen decay rate, the shedding rate, and the decay of the infectious host individuals at each individual patch. And I'll just note in passing here that, let's see, the L, I said before, that's an M matrix. So D naught plus L is going to be invertible, and in fact, it's going to be a non-negative matrix when we perform this inverse. So in fact, the R naught we're caring about here is really the spectral radius of a non-negative matrix. Okay, and that's a good thing, right? That's a well understood object. Okay, so as I said earlier, each patch has its own characteristics corresponding to the pathogen, and in particular, each patch has its own individual basic reproductive number R naught super K that's based on the patch specific parameters. Okay, and so it turns out that if the dispersal rate between the patches is much faster than the disease dynamics in the patches, it turns out that you can approximate R naught as a linear combination of the individual basic reproductive numbers. So it's going to be a sum k equals 1 to n of u sub k R naught super k, where this vector u is the right null vector of the Laplacian matrix L, normalized so that the sum of the entries inside of u is equal to 1. Okay, so L, as I said before, is an M matrix. It turns out to be singular by the way that we set things up. And so this U naught turns out to be an all positive null vector for the Laplacian matrix L. And so here's the really useful thing about this observation. This eigenvector U, this null vector, only depends on the network. Okay, so because it's governed by the matrix L, okay, and not on the individual disease dynamics across the different patches. And so what that means is we can study the influence of the network structure on R naught. Okay, and in some settings, this might be a really useful thing. We may not have a lot of good control over the level of invasibility in the individual patches, but we may have better control over the structure of the network connecting those patches. Okay, so for example, if it's a network of airports, for instance, you might decide you would like to, say, increase or decrease traffic from one site to another by controlling the network. This is something you can understand if you understand what's going on with this eigenvector u. Okay, that's kind of where I'm going with this. All right, so I just want to give you a sort of toy example to get you a little bit of the flavor of how the structure of the network can be influential on this value of R naught. Okay, so I have two pictures here, and let me just decrypt it a little bit. So I'm thinking here essentially of a path network. That's what the two directed graphs are depicting here. And in the left-hand picture over here, okay, I've got the vertex number two in red. Okay, so I'm thinking about that. The site number two, patch number two, is a hotspot for the disease. Okay, and the particular value we look at here, the R naught value in patch two is 10 times the R naught value for each of patches 1, 3, and 4. Okay, and now what we do is we allow an extra arc in the digraph, the arc going from 1 to 3. Okay, so we're allowing now movement from patch 1 to patch 3, and we're increasing the rate of that movement through this value M31. And the graph underneath of the picture here shows you what happens to the value of R naught. Okay, what we see is in the left-hand picture, the value of R naught is decreasing as we increase the rate of movement from patch 1 to patch 3. Okay, so that's good. And then I have a similar picture over here. We have the same basic path network, only now our hotspot, again 10 times larger than the others. Our hotspot is at patch 3. And we're going to increase the rate of movement from patch 2 to patch 4. And now look at the graph and see what happens. Qualitatively, the behavior is completely different from the left-hand picture. So now we see increasing the rate of movement from patch 2 to patch 4 causes the value of R naught to increase. And importantly, it takes us, as we increase this value of M42, it causes us increase from a value of R naught that's strictly less than 1. That's good, the good situation, to crossing that threshold and eventually becoming strictly greater than 1. Okay, so a lot of what I'm going to tell you about today is kind of the toolkit that helps us to understand these two different scenarios as we perturb a particular value inside the movement matrix. All right, so let me frame that with what I mentioned earlier. Imagine we've got our weighted directed graph that leads to actual values inside a movement matrix M. And let's suppose for concreteness that the movement matrix is strongly connected. So in other words, in terms of the diagram, I can get from any vertex in the directed graph to any other vertex in the directed graph by following a pseudo sequence of arcs. All right. And so then our Laplacian matrix is, as I said before, it's an M matrix. It's singular and it's irreducible because the directed graph is strongly connected. And so, great, we can use Perron-Frobenius theory for our M matrix to tell us that there's a unique null vector U that has all positive entries and whose entries sum to 1. Okay? And now what I want to do is I want to perturb the movement matrix M to generate a new movement matrix, say M tilde, whose digraph is still strongly connected. And of course, that's going to give us a new Laplacian matrix, L tilde. And I want to try and understand what's the structure of U tilde, the corresponding right null vector for L tilde. okay? And in particular, what I'm really after here, in terms of trying to understand the dynamics of the disease outbreak on this patch network, is there a good perturbation, M tilde, so that when I look at my approximation to the reproduction number R naught, that I come up with something that is smaller than the original value of R naught. Okay, that's really what I want to do. So I'm trying to perturb the network in a certain way to do something good with the vector U tilde so as to decrease the value of R naught. Okay, so let's try and think about this. A natural way of thinking about this is in terms of combinatorics, because we're talking about a weighted directed graph here. Okay, so our Laplacian matrix is singular. It has 0 as an algebraically simple eigenvalue. That just comes out of the basics of Arrhenius theory. And so, which is a classical result, I think about the matrix of cofactors for the matrix L, so that's the adjugate matrix. So L times the matrix of cofactors, that's going to be 0, the 0 matrix. And that's also true if I take the product the other way, the adjugate times L. And so what we can deduce from that is that the adjugate matrix is a scalar multiple of the outer product of the right null vector U with the left null vector, which is the all one sector. Okay. So let's think about that another way. Remember, the adjugate matrix is full of cofactors. So we're really saying that the entries in U are proportional to the principal minors of L order n-1. Okay? And fortunately, because we're in the setting of a singular M matrix with 0 column sums, there's a lot known about those minors. So I'll let C sub k be the principal minor formed by deleting the kth row and column of our Laplacian matrix, and that C sub k can be written combinatorially as follows. It's sum over what I'll call T in T sub k of W of T. So I have to unpack the notation here for you. So T sub k, that's the set of spanning entries rooted at vertex k. The W of T is the weight of one of these spanning entries. In other words, it's the weight of all of the arcs on that spanning entry. And spanning entry, if you don't know the definition, that's just a tree. It's directed, uses all of the vertices in our network, and it's oriented in such a way that all of the arcs in the directed tree are oriented towards vertex k. All right. And this is really a consequence of a slight generalization of the Kirchhoff's matrix tree theorem. Gives a combinatorial interpretation of these minors. Okay, so in some sense we now know what's going on inside this vector U in a combinatorial from a combinatorial perspective. Okay, and so U sub k. All right, well, that's going to be these C sub k's, and then I have, since I want the entries in the vector U to sum to 1, I have to divide by the sum of these cofactors, some of these minors, excuse me. And so, I want to try and analyze this a little bit. So let's fix an arc inside our directed graph, the arc going from J to I, so that the corresponding entry Mij in the movement matrix is strictly positive. And now I want to develop some notation. I want to think about these spanning entries rooted at vertex k, and they're going to come in 2 types. So W sub k superscript ij, that's this guy here. Okay, so that's going to be the sum of the weights of spanning entries that are rooted at vertex k that contain the arc from J to I. And then this guy here, W sub k super tilde ij, that's going to be the sum of the weights of the spanning entries that are rooted at vertex k and that do not contain the arc from J to I. And of course, it's easy to see that our minor, C sub k, can be written as the sum of those two numbers. And so then now this is sort of it's a bookkeeping exercise using what the quotient rule for derivatives, and a sample result. You can figure out the sign of the derivative of u sub k with respect to the movement matrix entry Mij. It's going to be the same as the sign of the difference between these two expressions. So I'll have a Wij sub k times sum of the W sub L tilde ij's, take away, and I just sort of reverse the role, take away W sub k tilde ij times the sum of W sub L ij's. Okay, and in particular, it's not very hard just analyzing that expression for a second, that if I is different from k, then the derivative of u sub k with respect to m sub ik is strictly less than 0. Okay, and the reason is when j is equal to k in this expression here, this guy, this w sub k super ij, when j is equal to k, this is 0, and so I've only got a negative contribution over here. So that's an example of the kind of using the combinatorial approach to get some understanding about what happens to this eigenvector u as you perturb a particular entry in the movement matrix. And so, of course, you can use that in analyzing the derivative of our approximation to R naught, the derivative of that approximation with respect to m sub ij. All right. So now I want to switch gears a little bit here and think about the problem in a slightly different way. So I want to think about U algebraically instead of thinking about it combinatorially, although I promise I'll later I'll come back and I'll try and connect the two approaches again for you. So let's go back to our Laplacian matrix L. As I've already said, it's not invertible because the column sums are 0, but it has what's called a group inverse. And I'll just give you a definition. So that's a certain type of generalized inverse. I'm going to call it L sharp. And it has the following three key properties. So L sharp commutes with L. That's what this first equation here says. If I take the product of one L sharp and two L's, I'm going to recover L back again. And if I take a product of two L sharps and one L, I'm going to recover L sharp back again. Okay, so this is the group generalized inverse for the matrix L. And it turns out, it's not very hard to show, that if I look at the product of L sharp times L, then that's equal to the identity matrix, take away the outer product of the null vector u, the right null vector u, written as a column, times the left null vector, the L1 vector, written as a row. Okay, and that observation about what L sharp times L looks like, it turns out to be quite useful in establishing the following formula. So here's the setup. Imagine that I have my original Laplacian matrix L corresponding, and that it's irreducible. And then I have a perturbed Laplacian matrix L tilde, so I'll write it as L tilde equals L plus E. So E you can think of as an error matrix, say. And that L tilde is also an irreducible Laplacian matrix. Okay. And now I want to think about the null vectors u, the right null vector that goes with L, and u tilde, so that's the right null vector that goes with u tilde. I want to think about those two null vectors where again I take the normalization that the sum of their entries is equal to 1. Okay, and what I would like to do is figure out how can I find u tilde from u. And here's the great news. There's a closed form formula for u tilde in terms of L sharp, our error matrix E, and the original null vector U. Okay, so U tilde is equal to the inverse of identity matrix plus L sharp times E, all multiplied onto this vector U. Okay, it's not very hard to show that, first of all, that the inverse that we're looking for exists for us, and that U tilde has that desired property. Okay, and if you ever looked at perturbation theory for stationary vectors and Markov chains, you'll see that there's a similar formula in the Markov chain literature. So the point is, if I know my Laplacian matrix L and I can capture its group inverse L sharp, then I can write U tilde in terms of U, and that's good news. All right, so let's try and work with this idea. So I want to set it up in a really simple way. Imagine that I perturb the movement matrix so that I'm going to just change one entry. Mij is going to change to Mij plus epsilon. Okay. So what's that? Well, that's going to give us our formula for L tilde as the old matrix L plus epsilon times E sub j minus E sub I times E sub j transpose. The E sub I and E sub j, those are just standard unit basis vectors. And the good news here, so this is, if you like, this is my error matrix capital E from the previous slide. Good news here is it's rank 1. Okay, and so we can use the Sherman-Morrison formula that we saw before, as well as the formula for U tilde that I just gave you, to figure out how do the entries in U change when I do this perturbation, and you can see it here. U tilde sub k, take away U sub k, is this expression here that's been built out of the entries in U and the entries in L sharp, and of course the value epsilon. Okay, so I've got a closed form formula for UK tilde take away U sub k. Okay, and so for example, I can capture, just by letting epsilon go to 0 in the usual way, I can capture the derivative of U sub k with respect to Mij as this expression here, minus U sub j times the kj entry of L sharp take with the ki entry of L sharp. Okay, so that's somehow giving us even a little bit more information than the combinatorial approach to the derivative that I told you about a couple of minutes ago. Better than that, I can also use this formula to figure out what's the change in R naught. So here's an important formula for us. R naught tilde take away R naught is equal to this expression here. It's not a pretty expression, but again, it's built out of the things that we know. It's built out of the entries in L sharp, the entries in the original null vector U, and then these local R naught values at the different hashes. Okay. So what I want to do is now try and get some utility out of this formula. And so before I do that, I did promise I was going to reconnect the algebraic viewpoint of L sharp with the combinatorial viewpoint that I gave you before on the entries in U. And I'll just say that in terms of finding L sharp, it's actually not that hard to do. You can get it by taking a certain principal submatrix of L that's of order n-1. You make a few small rank adjustments to that principal submatrix, and that gives you a closed form formula for L sharp. Okay, but let's see, the inverse of a principal submatrix of L that's of order n-1, well, that can be computed from the adjoint of that submatrix. And so I've already seen the connection before. The entries of L sharp can then be written in terms of certain minors of the Laplacian matrix L. And as we already saw, those minors can be written through the all minors matrix tree theorem as sums of weights of certain spanning inforsts in the directed graph associated with L. Okay, so I'm being a bit vague here, but the takeaway message I want you to remember here is that L sharp remembers a bunch of the combinatorial structure in our weighted directed graph. Okay, and so even though I presented it to you originally as sort of an algebraic object, generalized inverse, Even though we can use it in getting analytic information about the change in the null vector in the perturbation problem I just described to you, it also understands some of the combinatorics of the underlying network. Okay. All right. So I want to go back to the hotspot example that I gave you earlier, that toy example. So let's think about the following situation. Imagine I've got a strongly connected network on vertices labeled 1 up to n. And imagine that we have a special vertex L. I'm going to think of L as being the hotspot. So that the local R0 values for the vertices away from L are all equal to each other, and there is value little r sub 0. But that the local value of R0 at the hotspot L is strictly bigger than all the other R0 values. Okay? So that's the setup, and that's like the toy example that I described to you a few minutes ago. And now I want to do the following thing. I want to pick a pair of indices, I and j, and I want to increase m sub ij by a fixed amount. Okay, I'm going to change m sub ij into m sub ij plus epsilon. Okay, so I'm increasing the rate of movement from patch j to patch I. Okay, well, from our earlier formula, we can figure out what the change in the R0 value is. That's just our formula back again. It's slightly simplified by the fact that we have a single hotspot, so the R0 values are mostly equal to this little r sub 0, except for the R0 value at patch L. Okay, and so what we'd like to do, of course, we're trying to decrease the value of R0. All right. So we view the minus sign here. One of the things I might use as a strategy is to try and figure out which indices I and j should I pick so that the coefficient of interest here is as large as possible. Okay, so if this is large and positive, then I've got hitting this with a negative sign, and so I have a good shot at decreasing the value of R0 after perturbing in the ij position of my movement matrix. Okay, and so the point is, you just look at the formula. L sharp is giving you information on how you might be able to make a good choice of I and j. Okay, so let's look at a specific example. Here's my Laplacian matrix, and this is really just the Laplacian matrix for a path where all of the movement rates are equal to 1. Okay, and this really is a generalization of the toy example that I gave you a few minutes ago. All right, so here's our Laplacian matrix, and let's suppose that vertex L is our hotspot. Okay, and so you just go through and you analyze L sharp. Okay, the matrix L is quite nice. We can produce a closed form formula for L sharp, and here's what you find out. Okay, so if the hotspot L is bigger than or equal to n plus 1 over 2, then the expression of interest is maximized when I choose I equal to 1 and j equal to L. Okay, and here's the maximum value of that expression. On the other hand, if L is less than or equal to n plus 1 over 2, then that expression is maximized when I equals n and j equals L, and I've given you the maximum value. Okay, so really what we're saying here is if the hotspot is at vertex L, then what do we do to get the best change, the best decrease in the value of R0? Well, what we should do is we should pick the pendant vertex of our path that is farthest away from the hotspot, and we should increase the rate of movement from the hotspot to that pendant vertex. That change is going to give us the best possible change, best possible decrease in the value of R0. Okay, so that's just an example of the kind of analysis you can do with this L-sharp, and I'll also say that you can also understand the two examples that we saw are toy examples. The one where we had a bypass that gave us a decreasing value of R naught, and the other where we had an increasing value of R naught. You can also understand those examples by that technique. Okay, so I'll wrap it up here with just a few concluding thoughts. So just a recap, we've modeled our disease outbreak on a network of patches, and it has kind of two components to it. There's some combinatorial structure, but there's also some analytic structure as well. Okay? The advantage of the approach we've taken here is we're able to sort of parse out the influence of the combinatorial structure, the underlying weighted directed graph, and we can figure out its influence on the value of R naught. The techniques of combinatorial matrix theory, especially the matrix tree theorem, I mentioned a couple of times, are important tools in understanding the influence of the network on R naught. But we also have this group inverse going for us as another tool in our toolkit that helps us to understand network-based strategies for decreasing the value of R naught, which is measuring the invasibility of the disease on the network. So I'll just say, if you're really interested in the details, we have a paper on this. It's in the Cyan Journal of Applied Mathematics. And I'll just thank you very much for your attention.
Okay.
Participants, if there are any questions, please raise your hands so that we can handle.
John, you have a question?
Yes, sir. Yeah, sorry. Thank you, Steve. Excellent talk. I might have missed at the beginning. So the sort of combination of using these diagonal scalings in connection with the inverse of that M matrix, how do you know that they're only diagonal matrices that are sort of intertwined there and not sort of more general matrices?
So the idea is it really comes out of the way that you're doing this model of coupled ODEs. So you're capturing, so it's an SIR model, and you're capturing at each patch you've got sort of local dynamics of the disease. You go through you set up the system of ODEs, and then essentially what you want to do is linearize around the disease-free equilibrium. That's what gives you the matrix of interest. And so they're diagonal matrices because they're only capturing the information about, say, whatever the pathogen shedding rate in a particular patch.
And are there more general sort of models where you might have different kinds of interactions?
Sorry, you're breaking up. Can you try again?
Yes, of course. Are there sort of more general sort of assumptions where you might have sort of more broad interactions?
You mean just the path that I was talking about in my examples today?
Yeah, I mean, or more general interaction between patches.
Oh yeah, for sure. I mean, the theory goes through for an arbitrary network. So you take your favorite weighted directed graph. and have it be strongly connected so that the problem has got a bit of structure to it, and then away you go. So so I was focusing on these path type examples because there's something similar, and there's a sort of I think part of the initial interest in this is this model of cholera. You might think about a path as being like a river. Okay, so you've got a river. There's infected water that's traveling from upstream to downstream. You've got these communities on the river, and you want to figure out what's happening with this R0 value.
Okay, thank you. Again, great talk. Thanks.
Okay. So, any other question or comment? Yeah, I just want to know, you were talking about finding the right perturbation of the movement matrix. Steve, can you hear me? Can you hear me, Steve?
Yeah.
Okay.
I can hear you. You're breaking up a bit, but yes.
Yeah, so you were talking about finding the perturbation of the movement matrix. So what does it involve? I mean, is it a government policy thing, or is it scientific, or is it the actual movement of people from city to city, or how does one control it? It may be difficult, but how does one go about it?
Yeah, so it could come up in a couple of different settings. One example is a network of airports, and so imagine that you have a worldwide pandemic that's being spread through travel, and you wanna try and control the outbreak in some fashion. And so governments might decide, okay, you know what, we're going to close this airport, or we're going to restrict the amount of traffic from one place to another. And indeed, they do that, right? We have travel bans. So that's one possibility. The other thing that we were thinking about, sort of almost more philosophically, is going back to the cholera model. Imagine you've got some flooding that happens, okay? And you want to know, okay, if there's flooding that increases the flow rate from one patch to another, what's the effect on the invasibility going to be? So those are two possible examples where you have in the network example, you have the opportunity to control the network. In the river example, you can't control the flooding maybe, but you can at least figure out what the effect in terms of the R0 value is going to be.
Okay. Any other comment or question? If not, then let us thank Steve again for this very interesting Hans Schneider lecture. Thank you very much.
Thank you.
We'll just wait 1 minute or 2 minutes, 1 minute before going to the next talk. So, yeah, and just 1 minute we will wait. Okay, so I now welcome our next speaker, Professor TSS R.K. Rao, and he will give us a talk on orthogonality for biadjoints. So, over to Professor Rao.
Thank you, group, and give a talk at the conferences organized by Professor Manjuna Prasad and his colleagues. In spite of all the difficulties, I think it has really become December annual event for CINS. And the way these things have been very efficiently organized is a matter of pleasure to all of us. So I am going to talk today about this geometric notion called orthogonality. And this is an extension of the notion of orthogonality that one studies in Euclidean spaces or more generally in Hilbert spaces. So let me just read out my abstract and then I explain the notions involved using my board. So this is called orthogonality or biajoint. So an important direction of investigation in operator area of Banach spaces. So somehow my background objects are always Banach spaces as opposed to Euclidean spaces or Hilbert spaces where the regular operator theory gets done. But my operators are between Banach spaces. So one of the interesting questions is to perform standard Banach space theoretic operations on spaces of operators and ask if the resulting object is again a space of operators. Maybe not between the same Banach spaces, maybe between different Banach spaces. So since I have a very young audience, let me, for example, try to draw an analogy. Suppose you are working in group theory. If you take the normals of group and if you take the quotient, you always know that you again will get a group. Suppose instead you look at the setup or automorphisms of a group, that again becomes a group. Suppose you so that is a kind of question. So we look at things with certain property and take a quotient, appropriate quotient, and then of course you get a new object. But you wanted to say, is this new object is also in some sense like my previous thing. Previously, for example, I had automorphisms of a group, but I Is there a lag or a technical issue? I can't hear anything.
Yeah, there is no sound, first of all, and I don't know whether the slides are supposed to move or is it just one slide?
At the moment, this is one slide.
But in between,
recording progresses.
Yeah.
When the record, this is a recorded talk.
Right, I understand. But in between, there is no sound also. That's another problem. Yeah. In the beginning, it was okay, then it stopped. In between.
Also, in some sense, like my previously, for example, I had automorphisms of a group, but I performed a certain group theoretic operation. But now, the new object I get is also set up our automorphism, maybe on some other group. So these are the kind of questions which are quite interesting in various branches of mathematics. For example, even though I'm talking in functional analysis now, the example I drew is from algebra. You could ask the same question in algebra. So what I would like to do is in this talk to tackle this problem. That means do a certain standard operation in a class of objects and somehow realize that after you perform this standard operation, you again have a similar type of objects. That is the thing we want. So we tackle this problem to this well-known geometric operation called Birkhoff-James orthogonality. And the thing is that for non-reflective Banach spaces X and Y, for closed subspaces M of the space of operators between X and Y, we investigate Birkhoff-James orthogonality of an operator to the subspace with that of biadjoint. That is what is biadjoint D star star with the appropriate subspace of, I write it as M star star, but I explain to you what this means. So here, of course, again, the notion of an adjoint is not like that of a matrix or operator on the Hilbert space, but these are what are called Banach space adjoints. So you take an operator T, then you have this thing called T star, and then you perform the same operation again, you get something called T double star. And unlike the case of Hilbert spaces, somehow T and T double star are entirely different operators in the context of operators in Banach space T. So somehow the behavior of T versus the behavior of T double star can be dramatically different. So this is what we will do. So what I'm going to do before I go through my slides is to slightly give you an introduction of some of the terminology involved using my board. So here I said that the kind of things that I'm interested are in spaces X and Y, and they are non-reflexive spaces. So let me explain what this means. Okay. So generally, of course, if you start with a Banach space X, Banach space, then you can look at the space of all continuous linear functions, that is called X star. Continuous maps, which is also linear. Scalar valued continuous linear map X is denoted by X star. And this X star, of course, in its own right has a natural norm, and it again forms a Banach space. So, of course, you could repeat the same operation to take X double star. So that, of course, will be again space of all continuous linear functions on this. So this is called the second one, unbind one. And there is a natural way X can be embedded as in X double star. So that is called the canonical embedding. So I will not go into the details of the canonical embedding. Instead, what I would say is that if this canonical embedding is a non-two map, then such a Banach space is called reflexive. So if you know, for example, relations, then you will see that what we are looking at is you perform the operation phi, so that's kind of reflexivity. So X coincides with X double star under the canonical embedding, then such is called reflexive spaces. These are, of course, nice Banach spaces. These are, for example, the Hilbert space is actually a reflexive Banach space. Similarly, if you have studied measure theory or probability theory, you will see that for 1 less than p less than infinity, the space LP of the measure space is always a reflexive space. And so on. But it turns out that there are other classes of Banach spaces which are not necessarily reflexive. Not reflexive, that means this embedding X into X double star is a strict embedding. Then you would say that it's not a reflexive space, but they are quite natural. So I'm going to erase this and go to the next slide. So here is the other measure space that you have studied about, L1 of U, the space of all integrable functions. Or L infinity of U, the space of all essentially bounded functions. So these are, for example, very classical examples of non-reflexive spaces. Similarly, if you look at continuous functions on 0, 1, or more generally, continuous functions on a compact set omega, but omega is infinite. So these are Banach spaces are again non-reflexive spaces. So that somehow once you move away from the comfort of LP theory and only talk about L1 of mu but p is equal to 1 or p is equal to infinity and infinity of mu, or more generally continuous functions on 0, 1 or CF omega, these are all non-reflexive Banach spaces. So let me just show one more set of examples before we go back to our task. So these are non-reflexive mean infinite dimension. So a non-reflexive space is necessarily infinite dimension. Finite dimension spaces one can see easily are reflective spaces. So a non-reflective space is necessarily infinite dimensional. So for example, if I take an infinite dimensional Hilbert space, then you look at the set of all operators on this Hilbert space. That's a very important space that everybody studies in analysis. Operators on Hilbert spaces, various aspects of it. But this is not a reflective space. So similarly, there are naturally occurring objects inside BFX. Those are called C-star algebra. So A contained in B of it is a infinite dimensional C-star algebra. Then again, A is not reflective. So it is not so uncommon to come across spaces that are not reflective. Even though reflective spaces are nice, a lot of spaces on which we do analysis and we regularly use are actually also are non-reflective spaces. So one has to somehow also have a set of techniques which are applicable to non-reflective Banach spaces. So if there is any question or comment, I'll come back to it at the end of the talk. So at the moment, I'm now looking at my chat box and we will proceed with the talk. So finally, so let's look at X and Y non-reflective spaces. So let us look at now space of all bounded operators between X and Y. Bounded linear maps. So that of course is the usual operator norm. So norm of T is the supremum of norm of T of X, where X is in the unit ball. So my notation for the unit ball is to put it as subscript 1. So that's my unit ball. X is in X1. Okay. So that is the norm. So this thing will be space. But then if you have a T from X to Y, there is like in the case of Hilbert space, you can talk about a joint. So joint T star from Y star to X star, the arrows get reversed. By the formula, T star of any object Y star is, you simply look at T from X to Y and compare it to with Y star. Y star is from Y to the scalars. So this resulting object is now from X to the scalars. Let's say real scalars. So this is how you define T star. It turns out that T star is again a linear map. And of course, we'll have, like in the case of Hilbert spaces, we'll have the same norm as the norm of T. So that is T star. So like you do in Hilbert space theory, you can also define the corresponding adjoint, but of course now adjoint is unfortunately between different spaces. So this is not good enough for me to talk about T and T star, but I have to now do this operation once more. So that's what my biadjoint means. So now we got T star from Y star to X star. So of course these are Banach spaces. This is a bounded linear map, so I can perform the same operation again. T double star, and that is the X double star to Y double star. So that is somehow I originally started from X to Y, and by looking at this biadjoint, I got now maps between X double star and Y double star. But in the beginning, I talked about the canonical embedding. X actually sits inside X double star in canonical way. Y actually sits inside Y double star in a canonical way. And in some sense, this T double star is taken as an extension of the original operator T that was solved. Your original operator is between X and Y, and by performing this bi-adjoint operator, you'll be able to extend it to a bigger operator T W star. And of course, you can have a norm of T W star will always be the same as the corresponding T star, which is also the same as norm of T. So, like in Hilbert spaces, the norm does not change, but the new operator T W star is between larger spaces, is between X W star and Y W star. Since I'm assuming that my spaces are not reflective, X W star is necessarily bigger than it, Y W star is necessarily bigger than Y. So this is my notation then for the space of our operators between bi-adjoint, so X W star, Y W star. So this is kind of background that we need. And now I will close this and go back to my slides and present the rest of my talk. So now this is what I want to look at. The kind of operation that I want to look at on a real Banach space is the notion of orthogonality. So if you take non-zero vectors x and y, then you would say that x is orthogonal to y in the sense of this is the notion introduced by Markov and James. If norm of x plus lambda y is bigger than or equal to norm of x for all x. So the condition is that you want norm of x plus lambda y to be bigger than or equal to. You can quite easily, if you have a Hilbert space and by taking the square of the thing, if you remember, if you have the norm of length of the vector, if you take the square of the length, that will be inner product of the vector with itself. So if you do that and do this, expand it out, you will see that in the case of Hilbert spaces, if x and y are orthogonal in the sense that in inner product of x with y is equal to 0 in the usual sense, then x plus lambda y will always be bigger than or equal to norm of x for all lambda. And conversely, if x and y are vectors in Hilbert space, such that norm of x plus lambda y is bigger than or equal to norm of x for all lambda, it is then a simple exercise to see that the inner product of x with y must be 0. So this is exactly the original notion of orthogonality in case of Hilbert spaces, but in case of Banach spaces, it comes up something different. Okay. So this notion coincides with the usual notion of orthogonality in the case of Hilbert spaces, and unlike the case of Hilbert spaces, this orthogonality, this way of defined, is not symmetric or transitive. As you can see from the definition, this is not a symmetric quantity at all. Y need not be orthogonal to x because the condition is that x plus lambda y should be bigger than or equal to norm of x. But in several interesting cases, in particular when x is what is called a smooth Banach space, it does lead to geometric properties that are similar to those enjoyed in a Hilbert space. So that's why this notion is quite interesting to study when your space is not a Hilbert space. Then it's a different notion and it's an interesting notion to study. So by closed subspace Y, like in the case of Hilbert spaces, I can do this notion of what does it mean to say x is orthogonal to the entire subspace Y? Well, I would say x is orthogonal to the entire subspace Y to mean that x is orthogonal to Y for all Y belonging to Y. Well, I have to give a different notion because part P somehow in Banach space theory is reserved for linear functionals which vanish from a subspace, so that's called the n vector. So I will write it as a Y vector. That means all those vectors F such that x is orthogonal to Y for all Y belonging to Y. So then one of the important questions in Banach space theory and elsewhere is that if you know the specific space Y, then can you describe what is Y dash? Can you describe the orthogonal? The orthogonal, of course, will only be a set and will, of course, trivially have 0, but will not be a subspace because somehow this operation is not symmetric or transitive, so that Y sharp is generally only a set. But one would like to know is that if you know Y concretely, can Y sharp be concretely be described? So this is what I call the basic bi-adjoint problem. So X and Y are non-reflexive Banach spaces. You take a bounded linear map between X and Y. Then we just now saw that the bi-adjoint, of course, is now no longer between X and Y, but it's bigger spaces, X double star to Y double star. And of course, this taking the bi-adjoint is a linear map. So that, like in case of Hilbert space theory, you know that norm of T double star plus S double star is equal to norm of T plus S, or RT and S belonging to L of XY. Similarly, if you have a scalar, you will be able to bring out the scalar from the adjoint. Okay. So the question is now, you start with a closed subspace M of L of XY, and you have an operator T which is orthogonal to this closed subspace. In the previous slide, I defined this notion of what it means to say a vector is orthogonal to a subspace. Now, the question is, can one now describe the smallest closed in what sense I will describe, subspace containing all the operators M prime, the meaning of M prime is clear in the next slide, such that the bi-adjoint is actually So can one describe the smallest closed subspace M prime, that's what I want, containing M, such that T double star is now orthogonal to this new subspace M prime. Originally, we have this equation, and now we want to know that if I do a bi-adjoint of this, then what is this thing I get on this side? Can I describe the space that I get on this side? So that T double star continues to be orthogonal to this space. So this is somehow very similar to very classical theorem in the theory of operators on Hilbert spaces on study called the one-Neumann double commutant theorem. So somehow one-Neumann double commutant theorem in C-star algebra theory, Hilbert space theory, will tell you that if you start with a C-star algebra subspace of the space of all Hilbert spaces, a space of all operators on a Hilbert space, then you look at all operators which commute with your original algebra, that is called the commutant. Then you look at all those operators which commute with the commutant again, that is called the double commutant. And one Neumann theorem says that double commutant is nothing but the closure of what we have started with in the weak operator topology. So this is somehow analogous in the spirit of one Neumann theorem. We are asking a similar thing, which would say that you have a subspace M and you have a T which is orthogonal, and now you do the bi-adjoint. Can you now describe the subspace to which this bi-adjoint is orthogonal? Okay, so let us go back to the slide. So, of course, the problem that I have formulated in the previous slide, of course, is too general, it's too huge. I mean, I'm hoping that by formulating this general approach, one has the scope of doing a large number of things. But of course, one has to start with a very modest way. So the modest approach is a more fixed one familiar subspace M, and then start working. So the very space is Y, right? So let us take a closed subspace Z of the range space and look at now only operators which are domain X but valued only in Z. So that will be, of course, a closed subspace of the space of all operators from X to Y. So that is the subspace, specific subspace I want to do. Then the target space, that is the M prime that I am looking at, I have a guess I can do it. The target space one wants is, now this is something I need to explain, so I just do a little bit on my board and come back to the slide. So I have this subspace of Z contained in Y, and then of course I have looking at operators from X to Z. That's what I call it as my M, subspace of X to Y. So of course if that is contained in Y, then there is this natural object called Z curve that you look at in Y star, namely all those elements in Y star which vanish on Z, Y of Z is equal to 0. So this is a popularly called NF. Again, somehow people are so fond of notations. If you go back to Hilbert space theory and you take a subspace Z as a Hilbert space, what I have written out is really Z curve in the notion of a Hilbert space. But even in Banach space theory, one is so fascinated by the Hilbert space analogy, you continue to call it as Z curve, even though there is no orthogonality that you could see. So this is called any factor. Now, of course, Z curve is a closed subspace of Y star. In fact, it is what is called a weak star closed subspace. And then one can look at the same operation once again. Look at that per. So this now will be then all the tau in Y of the star such that tau vanishes on Z. So that is called the binary. And again, there is some natural sense here. Z is always contained in Z as well. And if Z is not reflective, that's what I'm going to issue, because throughout my spaces are not reflective, then this is a proper inclusion. So that is okay. So that is the relation shape between Z and the Z curve and the bi-inherited Z star. And I'll just do a little bit more writing before turning back to my slides. So that now if you have an operator T from X to Z now, that is subspace of Y, then T star of course will only take you from Z star to X star, but T W star will take you back again from now X W star to this time it will actually take back Z double curve that I have described inside Y W star. So T W star will actually take you back inside this. Alright. Now of course there is just one more thing I want. So there are nice kind of operators. You have already seen this in Hilbert space theory, compact operators. So which continues to be nice even in Banach spaces. So if T is a compact operator, that means the image of the unit ball is a pre-compact set in the range. That's the definition. If T is a compact operator, then T W star is actually nice. It only takes you back only until Z. Z double curve will not come into picture at all. If the original operator is valued in Z, then compact operator, then T W star, which will also be a compact operator, but then it just puts you back inside Z. So T W star is generally considered the compact operator, which extends to the original compact operator, T from X to Z. So somehow things work very nicely in even when you don't have Hilbert spaces, the corresponding analogies keep working. So we call this as a canonical identification. So I'm assuming that that is also not reflective. Then of course I can start with S W star which is always belonging to S of x, z. That's a proper subspace of operators from x of star taking values in z developer. Under the appropriate assumptions, one can see that this subspace is actually dense in the weak star operator topology of this entire space. So what I would like to do is really get to my orthogonality problem in the following sense. So let me anyway just do a motivation via the quotient now. So if z contains y is a closed subspace, and if you know that y is orthogonal to z, this is actually equal to saying that when you look at the quotient space y over z, then the norm in the quotient space, of course, is distance from the vector to the subspace z. That is the norm. So that is the quotient norm. And the quotient norm should be actually equal to the norm of the vector y. That's all orthogonality means. Orthogonality in terms of distances means. Now, one can, of course, identify what is the bidual of the quotient space y over z, and it is actually nice. This is y of the star quotiented by the subspace z developer that I talked about. And since the canonical embedding of a space is bidual in an isometry, you can actually very easily see that the distance between a vector y and z is really same as y and z developer. In other words, if you sort a vector y in y, and if it is orthogonal to the subspace z, it's automatically orthogonal to the subspace z developer. So this is somehow another way of motivating what I am thinking. So the quotient formulation. So in terms of the quotient formulation, then distance between t from L of x z is the same as the length of the operator t. And my question is, when can you say that the distance between t double star and the corresponding operator space now is the operators from x double star to z double is equal to norm t double star? That's what I wanted to ask. But norm t double star is same as norm t. So clearly, I am asking, when are these two distances the same? So our quest actually boils down to something about a minimax problem. So if you remember, distance is what is called infimum of the object, whereas norm is the supremum of vectors. Now I have defined norm t is supremum of norm of t of x, where x runs in the unit ball, whereas the distance is simply infimum of norm of t minus s, norm of the operator t minus s, where s comes from L of x. So this is really a minimax problem. My question is that if you have this minimax problem, can you also solve this minimax problem? So these questions are also interesting for people who work in optimization theory, because in some sense this is also related to the optimization question. So here is our approach is to fix a domain x and solve the problem for all spaces x and y, and for some operators and certain subspaces z and y. And in the process, we briefly indicate the connection between very famous theorem of Rajendra Bhatia and Peter Stamper, and of course minimax theorem, and what comes into play is also the quotient linking property. So let me then indicate my connection with what I call an extended Bhatia-Stamper problem. And this would say that if you have Bhatia and Stamper have proved this in the context of inverse spaces, finite dimensional inverse spaces. So the question is that if you have two operators t and s from L of x, y, and t is orthogonal to s in the sense that we have defined orthogonality, then is there a vector x naught in the unit ball of x, that is the unit vector, such that t attains its norm at this point, and t of x naught is now orthogonal to s of x naught. And the positive answer in the case when x is equal to y is equal to a finite dimensional Hilbert space was given by Bhatia and Stamper in their famous paper in probably 2009. And since then, it has attracted a lot of attention. Several people have tried to work out various ways of generalizing the Bhatia-Stamper theorem. And what I'm saying today is in some sense also a generalization. So let me just put one more slide and stop it here. So the question is that now I have a closed subspace for this entire subspace. And I ask now the question, is there a vector x naught such that norm of t is equal to norm of t of x naught? And t of x naught is now orthogonal to the entire subspace. So instead of working with two operators, I have given this. So in fact, some of my answers to this have appeared in paper in numerical function analysis and operator theory, which has appeared in the October issue of, so this is the month, November, so October issue of that journal. And so here is the general problem that I have indicated, namely, now I want to ask the same question with TW star. And the main theorem is that if you take a compact operator T and if it is orthogonal to the space of all z value operators, and if you know that somehow the input program formula is valid, then you will naturally get a point such that T star of lambda is orthogonal to Z. So this is the extended version of Bartlett-Sembler theorem, and it gets valid without, when you have a compact operator, you can do it without much difficulty. So thank you for your attention. It has always been a pleasure to be.
Okay, thank you, Professor Rao, for this talk. So, are there any comments or questions from the audience?
Participants, please raise your hands if you have any questions. I think there are no questions, sir.
Okay, so if there are no questions, I think we'll thank again Professor Rao for the talk and then conclude this session. Thank you very much.
Thank you.
Thanks a lot, professors, for such a nice talk. I also thank Professor Bapat for chairing this session. We now have a short break. The next session will start exactly at 10:40.
Thank you, Krista. Thank you, everybody. Have a good day.
Thank you, sir.
Too late evening.
That's right. It's now 9 p.m. here. I don't think I would keep awake longer. Okay, then. Thanks a lot. Bye-bye.
Okay,
Have a good day.
thank you.
Welcome back, everyone. In this session, we have with us Professor S. Arumugam from Kalasalingam Academy of Research Education, Tamil Nadu, India. He has served as a referee for research papers in several national and international journals. He is an editor-in-chief of AKC International Journal of Graphs and Combinatorics. He has been conferred Lifetime Achievement Award by GATR Malaysia during the closing ceremony of 4th Global Conference on Business and Social Sciences held in Dubai. His research interests are network analysis, graph theory and applications, fuzzy logic and its applications to pattern recognition, topology, and list goes on. So today he will be delivering a talk on nullity of a graph. Another speaker of this session is Professor Balaji Ramamurthy from Indian Institute of Technology, Chennai. He has published many research papers in linear algebra and optimization journals and complementarity problems and in distance matrices. His research areas are complementarity problems on symmetric cones, spectral properties of non-negative matrices and their generalizations, etc. Today he will be delivering a lecture on generalized Euclidean distance matrices. To chair this session, I request Professor Pradeep G. Bhatt from Manipal Institute of Technology, Mahi, Manipal, to chair this session. Over to you, sir. I request Professor Pradeep G. Bhatt, please chair the session, sir.
Okay, good morning, sir. Arumugam, sir. Hello.
Yes, I'm available.
Yeah, welcome you, sir. You can start now.
Thank you. So my lecture has been recorded already. Let us see here. So I'm happy to be a part of this conference on linear algebra and applications. And I shall present a talk on nullity of a graph, which is having significance from the chemical point of view. We start with a simple graph of n vertices, and suppose the vertex set is u1, v2, vn. Naturally, the graph can be represented by a matrix, the adjacency matrix of the graph, where ith entry is 1 if the edges v and v are adjacent and 0 otherwise. It's a symmetric binary matrix of order n. And therefore, the eigenvalues of the matrix are real. So I order the eigenvalues lambda 1 bigger than lambda 2 etc. up to lambda n, which is called the spectrum of the graph. It can also be written as lambda 1 lambda k, where lambda 1 lambda 2 lambda k are distinct eigenvalues, and mi is the multiplicity of lambda I. So both notations are common. Okay. So given the spectrum of the graph, I just want to see whether 0 is in the spectrum. Okay. So that is the concept. So the nullity of the graph denoted by eta g is the algebraic multiplicity of 0 as an eigenvalue. So if eta g is 0, it means 0 is not an eigenvalue. That means the matrix AG is non-singular matrix. So in this case, I say that the graph G itself is non-singular. If eta G is greater than 0, then it means that 0 is an eigenvalue of the matrix, and therefore the adjacency matrix is singular, and therefore I call the graph also singular. Okay? So nullity depends on whether the adjacency matrix is singular or not. If the adjacency matrix is not singular, nullity is 0, and otherwise nullity is greater than 0. Okay. This is important because for a bipartite graph, when the graph corresponds to an alternate hydrocarbon, it has been proved that if eta g is greater than 0 or equivalently the graph is singular, it implies that the molecule which such a graph represents is unstable. So 0 is present as an eigenvalue means that the corresponding molecule which the graph represents is unstable. And therefore, experts in chemistry are interested in obtaining a characterization of graphs for which eta g is 0 or equivalently eta g greater than 0, because that will help them to identify molecules which are unstable. Okay, so that's a significant problem which was first posed in 1957 in a paper by Collatz and Sinogovitz. Characterize graphs for which the nullity is 0 or equal to nullity greater than 0. So this problem still remains unsolved. Okay. So we have made substantial progress. The general problem of characterizing graphs for which the nullity is 0 is still an unsolved problem. Okay. For this purpose, I will present a classical theorem given to Sachs, again a chemist, which gives a method of computing the characteristic polynomial of graph purely in terms of graph theory without going to determinant and evaluation of determinant. For this purpose, we introduce the concept of elementary subgraph. Take a graph G and H is subgraph of G. H is called an elementary subgraph if every component of H is either a K2 or a cycle. So the graph is the elementary subgraph is a collection of single edges and cycles. That's all. It's a collection of single edges and cycles. So it is connected to the graph. Every component is either a single edge or a cycle. I denote by CH the total number of components and RH the number of components which are cycles. Okay. So CH is the total number of components in the elementary subgraph and RH is the number of cycle components. With this, the coefficients of the characteristic polynomial of the graph can be computed using the elementary subgraph. So the characteristic polynomial is sigma ai x lambda over I varying from 0 to n. The ith coefficient of the characteristic polynomial ai is given by this formula. The summation here runs over all elementary subgraphs of order I. So for each elementary subgraph of order I, compute minus 1 power Cs 2 power Rs. Whereas I already said Cs is the total number of components and Rs is the number of cycle components. So sum it up over all elementary subgraphs of order I, that gives the coefficient of the characteristic polynomial. So this gives the characteristic polynomial. Okay. So the characteristic polynomial of the graph can be computed using elementary subgraphs. Okay. Now, suppose the graph is bipartite. Then every cycle is of even length. Therefore, we shall not have an elementary subgraph of odd order, because every component of the elementary subgraph is single edge which has 2 vertices, or a cycle which has even number of vertices when the graph is bipartite. Therefore, the order of every elementary subgraph becomes even. So there is no odd order elementary subgraph. That means for odd power, the coefficient A becomes 0. That means the characteristic polynomial has only even powers of lambda, which means whenever lambda is in the spectrum, minus lambda is in the spectrum. So for a bipartite graph, the spectrum is symmetric about the origin. Okay? So whenever lambda is present, minus lambda is also present. So in particular, if the bipartite graph is of odd order, then when you pair my lambda minus lambda, then what remains will be 0. Therefore, if G is a bipartite graph of odd order, then 0 is in the spectrum. Therefore, nullity is greater than 0, and therefore, such a chemical molecule will not be stable. Okay. So for bipartite graph, we have a nice method of deciding. At least when the graph is of odd order, 0 is in the spectrum. If it's of even order, both are possible. 0 may be in the spectrum or 0 may not be in the spectrum. That is about bipartite graphs. Okay. We should have the trivial observations first. If a graph has an isolated vertex, trivially nullity is greater than 0. Because if you have an isolated vertex, the corresponding row in the matrix is completely 0. Because the vertex has no neighbors. So one row is completely 0, and therefore 0 is definitely an eigenvalue, therefore eta is greater than 0. So whenever the graph has an isolated vertex, it's trivial that eta is greater than 0. Again, I call two vertices as twins if they are non-adjacent, but exactly the same neighborhood is there. Both vertices usually have the same set of neighbors. They are themselves non-adjacent, but they have the same set of neighbors. Then such pair of vertices are called twins. So if you have two twins, you can immediately see that in the adjacency matrix, the row corresponding to U and the row corresponding to V are identical. Okay? Because they have the same set of neighbors. One will be there in exactly the same place. Here they are non-adjacent. Therefore, no other problem. So when you have two twins in the graph, then the corresponding two rows in the adjacency graph, in the adjacency matrix, become identical, and therefore again 0 becomes an eigenvalue, and therefore eta g becomes greater than 0. So if a graph G has a pair of twins, then eta g is greater than 0. These are some trivial observations that help you to decide whether nullity is greater than 0. Fine. So obviously, nullity is the whole n, if and only if the graph is only isolated vertices, k and bar. Okay? If the graph has only n isolated vertices, the adjacency matrix identically is a 0 matrix. And therefore, 0 is an eigenvalue with multiplicity n. And that's only eigenvalue. So n of g, eta g is n, if and only if g is k and bar. For a path, if it is even order, the nullity is 0, and odd order, the nullity is 1. It comes immediately from our previous observation that for a bipartite graph of odd order, nullity is greater than 0. Pn is trivially a bipartite graph, no cycles are there. So for a path, if it is odd, nullity is 1. If it is even, nullity is 0. For a cycle, if n is 0 mod 4, the nullity is 2 and is 0 otherwise. So this is a simple example of graphs for which the nullity is known. Okay. So in terms of the order n, the bounds for the nullity is that if this is not the totally disconnected graph, the nullity is between 0 and n minus 2. Okay. The nullity is between 0 and n minus 2. It cannot be n minus 1. It cannot be n minus 1 because if nullity is n minus 1, n minus 1 eigenvalues are 0. But you see, we have a symmetry graph and the main diagonal is 0. Therefore, the sum of the eigenvalues is a trace of the matrix that is 0. So if n minus 1 eigenvalues are 0, the nth eigenvalue also will become 0. Therefore, if G not equal to Kn bar, n minus 1 cannot be eta G. So eta G is between 0 and n minus 2. It's completely characterized when it is n minus 2. So eta G is n minus 2 if and only if the graph G is the complete bipartite graph plus some isolated vertices. Okay. Eta G is n minus 2 if and only if the graph is complete bipartite graph with some isolated vertices. It's completely characterized. Okay. Similarly, the authors Chen and Liu in 2007 completely characterized graphs whose nullity is n minus 3. So nullity is n minus 3 if and only if is a complete tripartite graph together with isolated vertices. Okay, a complete tripartite graph, three parts, and all of them are mutually adjacent, and each part is independent. It's a complete tripartite graph together with some isolated vertices. This is necessary sufficient condition for the nullity of the graph to be equal to n minus 3. So from above, n if and only if Kn bar, n minus 1, no graph, n minus 2, complete bipartite plus some isolates, n minus 3, if and only if complete tripartite with some isolates. What about n minus 4? That also has been completely characterized, but we need some notations. So complete for determining graphs with nullity n minus 4, we need to introduce some families of graphs. So I take an R-parted graph, where R partition is x1, x2, xr, and cardinality of the xi is ni. That is, the graph is partitioned into all independent sets. The independent sets have cardinality ni. Okay. Now, if each vertex xi in xi is joined to each vertex in the next parted set xi plus 1, where I varies from 1 to r minus 1, then the resulting graph is called a chain-like r-parted graph. So you can imagine a path on r vertices and an independent set sitting in each vertex. So you have two independent sets joined everywhere. Next to independent set joined everywhere. So if the independent set is synced to a small one vertex, it becomes a path. That's why it's called chain-like r-parted graph. So n parts of n sets of independent vertices, x1 is joined with every vertex in x2, x2 is joined with every vertex in x3, and so on. xr minus 1 is joined with every vertex in xr minus 1, xr. This is denoted by the symbol P suffix n1, n2, nr, where ni is the choice of xi. Mod xi is ni. So it's a chain-like r-parted graph. So just a notation. If r is bigger than or equal to 4, in the chain-like graph, you join every vertex of x2 to every vertex of x4. One more thing is joined. So it looks like a triangle and a path. x2 and x4 are completely joined. This graph I denote by the symbol P superfix 1. There's one more extra has come to indicate that. One more extra joining between x2 and x4 will have come. So this family of graphs have denoted by the symbol P in the suffix N1 and N2 are indicating the sizes. Superfix 1 shows one pair of particles as with in addition joint. Okay, this is a symbol of for a family of graphs. One more, if R is bigger than or equal to 5, you join S1 with all the vertices in S4 as well as S5. So two joinings coming in the linear chain. So this to indicate two joins have come, I have put 2 in the superfix. So it's another family of graphs. All of them are R-parted graphs. Okay? What is a chain-like thing? The one is by one joining, the next one is by two joining. With this, for R bigger than or equal to 6, from this, make one more joining between x6 and x4. Okay? In 2, you put one more joining between x4 and x6. The resulting family I indicate by putting superfix 3 on the top. Three joinings have taken place in addition. With all this notation, we are able to say the nullity is n minus 4 if and only if it is a complete R-parted graph with R equal to 4. Or the chain-like graph with R equal to 4 or 5. Or chain-like with one additional joining when R equal to 4 or 5. And chain-like with two additional joins when R equal to 4 or 5. And chain-like with three additional joins when R equal to 6. Beyond R equal to 6, it is not n minus 4. So your complete characterization of graphs with nullity n minus 4. Okay? This is a little complicated. We have several families of graphs coming in n minus 4. Actually, 5 families are coming. Okay. The complete by a 4-parted graph, the chain-like thing, chain-like with one join, chain-like with two join, and chain-like with 3 joins. These are precisely the family of graphs for which theta g is n minus 4. N minus 5 also you have completed, but it is more complicated. It's open for n minus 6 and n minus 7. All these have appeared in the paper by Chen and Liu, published in 2011. So on the upper side, some progress has been made. Okay. Starting from n, then n minus 2, n minus 3, up to n minus 5, they have completely got all graphs with corresponding nullity value eta g. Okay. But from the lower side, it is completely open. Which graphs eta g is equal to 0? That's a fundamental problem for chemistry. Okay. For which graphs nullity is 0? That is, the graph is non-singular. That's a fundamental unsolved problem. For which graphs eta g equal to 1? That's another interesting problem. And so on. So nullity of graphs with nullity given value is to be investigated. So the other bounds for nullity in terms of other graph theory parameters. I will just indicate 2 of them. A click in a graph is a complete subgraph. Complete means every pair is joined. A triangle is a complete graph of order 3. So you take a graph, look at complete subgraph sitting inside. Such a complete subgraph is called a click. And the maximum size of a click in the graph is called the click number of the graph. So click number of the graph is the maximum order of a complete subgraph of G, of a complete subgraph of a given graph G. That is the click number. And it has been proved that the nullity is bounded above by n minus omega g, where omega g is the click number of the graph. So it gives an upper bound, another upper bound for the nullity which is much better than the previous boundary n minus 2. That's a corollary now. For a bipartite graph, the clique number is 2 because bipartite graph doesn't contain odd cycles, doesn't have triangles. So for a bipartite graph, the clique number is 2. So eta g less than or equal to n minus 2 comes as a corollary. Okay. So this is a more general bound for arbitrary graphs in terms of the clique number. Another bound is in terms of the girth of the graph. The girth of a graph is the length of the smallest cycle in the graph. Length of the smallest cycle is called the girth of the graph. If the girth is congruent to 0 mod 4, then eta g is bounded above by n minus girth plus 2, and otherwise it is bounded above by n minus girth. Okay. Fine. So this is another bound for the nullity of a graph in terms of the length of the smallest cycle in the graph. So these are some known bounds for the nullity of a graph. In these two bounds, interesting unsolved problem is characterize graphs for which equality holds. The extremal graphs for these bounds is to be determined. Okay. So that's how I put extremal graphs. In terms of diameter also we have a bound. Diameter is the maximum distance between two vertices in a connected graph. The maximum distance between two vertices in a connected graph. For example, for a complete graph it is 1. For a complete bipartite graph it is 2. For cycle it is n by 2, very near to n by 2. So in terms of diameter, the nullity is bounded above by n minus diameter of g if the diameter is even, and n minus diameter of g minus 1 otherwise, if the diameter is odd. This is another bound for nullity in terms of the parameter diameter of the graph. So I have produced 3 upper bounds for nullity in terms of other graph theoretic parameters. For all these bounds, the extremal graphs have to be determined. Okay. Now, from the application perspective, I shall give some graph transformations which does not disturb the value of the nullity of the graph. This is very useful, especially from application perspective. Okay. So I'm going to give some graph transformations. The first transformation of type 1 is, suppose the graph has a vertex of degree 1. It is a unique neighbor. Okay, a vertex of degree 1 has a unique neighbor. Remove those two vertices from the graph. So remove a vertex of degree 1 and its neighbor. You get another graph, H. And the theorem says that both G and H have the same nullity. It's very interesting. The nullity is preserved by the operation of, or by the transformation of, deleting a pendant vertex and its neighbor. Okay? Deleting a pendant vertex and its neighbor does not alter the value of the nullity of a graph. Okay? Fine. This has far-reaching consequences. For example, if you take a tree of order n, I can immediately tell you whether it is non-singular or not. Just completely I can characterize trees which are non-singular. There is open for general graphs. The method is simply apply this transformation repeatedly. Because tree has a lot of pendant vertices. A tree has a lot of vertices of degree 1. Keep removing degree 1 vertex and its neighbor. That is transformation of type 1. So start from a tree, apply transformations of type 1 repeatedly. Okay? So start from a tree of order n and keep on applying transformations of type 1. If you apply transformations of type 1 repeatedly, you will get a tree of order n. And keep on applying transformations of type 1 repeatedly. Okay? So start from a tree of order n and keep on applying transformations of type 1. If you apply transformations of type 1 repeatedly, you will get a tree of order n. And keep on applying transformations of type 1 repeatedly. Okay? So start from a tree of order n and keep on applying transformations of type 1. end with the empty graph, then the tree is not singular. Otherwise, it is singular. See, it's depend only if. Okay, it's depend only if. For example, take P4. B1, B2, B3, B4. B4 is dependent, B3 is a neighbor. Remove both of them. Remove both B4 and B3. I get simply H, B1, B2. Now B2 is dependent. Remove the pendant and the neighbor. Close. The graph becomes empty graph. So I conclude P4 is non-singular. Path on 4 vertices. If you take a path on 3 vertices, what will happen? B1, B2, B3. B3 is dependent. Neighbor is B2. Remove them. You get a single vertex. You don't get an empty graph. So P3 is non-singular. Okay, P4 is singular, P3 is non-singular. So this method is very efficient and algorithm to decide whether a tree is singular or non-singular. Just when for a tree eta g is greater than 0, we have if and only here. Okay? Fine. Eta g is 0 if and only if T can be transformed to the empty graph by applying transformations of type 1 repeatedly. This has been proved very recently in 2020 by Ma and Z. A very, very elegant, comfortable way of checking, at least for some families of graphs. Okay. Another operation of this type is the second type of transformation. Suppose your graph contains a path P4, B1, B2, B3, B4, where the internal vertices B2 and B3 are degree 2. Nothing goes up from that part of the path. See, a path on 4 vertices sitting in the graph. The middle 2 vertices are degree 2. Okay, nothing goes up and above in that path. You take such a path, suppose such a path exists. Okay, now your transformation is remove this path and just put the edge B1, B2. Okay, remove this path and just put the edge B1, B4. Right, the two vertices I throw out. Right, so remove the path, replace it by a single edge B1, B4. This is another graph transformation. And what has been proved is that in this transformation also, nullity is not getting disturbed. Okay? Nullity is not disturbed by applying this transformation. So this is the second type of transformation which does not disturb the nullity of the graph as reported in this paper. If they are dealing with unicyclic graphs, for unicyclic graphs, they took 1 and 2 as operations. So using the operations 1 and 2, they have proved that if G is a unicyclic graph, unicyclic means the graph has exactly one cycle. One cycle with so many trees attached to it. Okay, such a graph is called a unicyclic graph. So if this is a unicyclic graph, then G is non-singular if and only if G can be transformed to C3 or C5 or C6 or the empty graph by repeatedly applying transformations of type 1 and type 2. Okay, so the two transformations are very, very significant, especially from algorithmic perspective. You can easily adapt it and apply it to the graphs. So they have completely settled which unicyclic graphs are non-singular. Okay? You simply apply transformations of type 1 and 2 repeatedly, you end up with one of these 4 graphs. C3, C5, C6 or cannot. Then the graph is non-singular. It is completely solved for unicyclic graphs. There one more transformation of that type. If you have a cycle C4, where again the middle vertices have degree 2, you can remove the entire cycle. This also doesn't disturb the nullity of the graph. So they have recently developed three graph transformations which do not affect the value of the nullity of a graph. Okay. Good. When there are cut vertices in the graph, then we can look at the components separately and see whether it is of help in determining the nullity. That has been reported in the paper that appeared in linear algebra applications in the year 2012 by Gong and Su. If a graph has order n and is the cut vertex, you remove the cut vertex, the graph is split into several components called the components G1, G2, Gk. If I know the nullity of the components, can I say anything about the nullity of the whole graph? That is what these people are trying in this paper. Okay, so if we take a graph with a cut vertex and the components are G1, G2, Gk. Okay. What I have proved is, if there is one component G1 such that nullity of that component is nullity of that component plus the vertex minus 1. This is the component, put back the vertex V. Okay? In the component, put back the vertex V. If eta G1 is equal to eta G1 plus V minus 1, then nullity of the whole graph is simply eta G1 plus eta G minus G1. That's the remaining components. Okay. So if one component has this property, we are comfortable. So in particular, if there is one component for which this relation is true, then the nullity of G is simply nullity of G minus V minus 1. Okay? That is simply you take the sum of the nullity of the components minus 1. Because there is at least one component satisfying this property. That's important. Okay? Because components is a much smaller graph, eta G can be easily found. So this is what the authors tried. Okay. And the people talk about graph operations. For a tree, they have taken the line graph of the tree. Line graph means line graph of a graph G is the edges of the graph become the vertices. And the vertices towards are connected by an edge with the corresponding edges are adjacent in the original graph. Such a graph is called the line graph of the original graph. And it has been proved that if T is a tree, then its line graph is either non-singular or the nullity is exactly 1. Okay? So this has some significance. They are able to prove that for the class of trees, the nullity set is 0 or 1. By that I mean, if you take any member in this class, its nullity is either 1 or 0. And it is 0 when the number of bits is even. So it's completely cut like this. Okay. Then there's another important concept from chemistry coming called energy of a graph. Energy of a graph is the sum of the absolute values of the spectrum of the graph. Take the eigenvalues of the graph, take the sum of the absolute values of the eigenvalues of the graph. That's called the energy of the graph. It's connected to the energy of a chemical molecule. Okay? Orbital chemical energy of the molecule, from where the terminology comes. And chemistry people observed that. So quantum chemistry people observed that the energy is a decreasing function of nullity. See, what does it mean? Energy is a decreasing function of nullity. It is suggested by experts in quantum chemistry. Okay. What is the meaning of this statement, or how to formulate this as a mathematical statement? The energy is a decreasing function of nullity. See, for any graph G, I have a parameter energy. Energy is a number. Okay? Energy is the real number, which is the sum of the absolute values of the eigenvalues of the graph. Nullity is an integer. What is the algebraic multiplicity of 0 as an eigenvalue? So if EG is a rational number, or even irrational number, is a real number, nullity is an integer, so graph has two parameters. And chemistry people are saying energy is a decreasing function of the nullity eta G. So how to formulate it as a mathematical statement? This is what Gutman and Tenterflow tried in 2016. It's in the same match. It's a spelling mistake. Communications, mathematics, and computational chemistry. So they felt one possible formulation is if G1 and G2 are two graphs, if eta G1 is bigger than eta G2, then energy G1 is less than energy of G2. Okay? This is how they looked at one possibility. When nullity goes up, energy comes down. Okay? When nullity goes up, energy comes down. So they take two graphs such that the nullities compare. Eta G1 is bigger than eta G2. Then energy of G1 is less than energy of G2. This is how they have formulated the whole quantum chemistry property. The whole quantum chemistry property suggested by the chemistry people has now been formulated as one way of formulation is like this. There may be another way, but no one has checked the validity of this conjecture. It's another major unsolved problem. Connecting nullity and energy of a graph, both are chemically important parameters. They have verified this statement for the family of banana trees. It's a family of trees. What is a banana tree? You take a lot of stars. Star means one center and so many leaves. Take K stars. Put a common vertex and join the vertex to centers of the stars. It will look like a banana tree, okay? Take K stars, put an additional vertex, join the additional vertex to all the centers of the stars. Such a tree is called a banana tree. So for the family of banana trees, the authors have verified this statement. This is the content of the paper by Gutman published in 2016. But the general case is a big unsolved problem. So two major unsolved problems in nullity is this relation between nullity and energy, and when nullity is zero, okay, for which graphs nullity is zero, there's a major unsolved problem. Okay. So the whole conjecture remains open, and people say solution has significant influence in quantum chemistry. Okay. Other general directions to look at is compute eta G for specific graph classes. Then try to find bounds for eta G in terms of other graph theory parameters. They have done it for diameter, click, and depth. But there are so many other graph theory parameters for which nullity is possibility related. We don't know. And in general, how does nullity behave with respect to graph products? There are operations like joining, Cartesian product, and so on. Then characterization of graphs with given nullity. Which graphs have nullity 1? Which graphs have nullity 2? Such problems are all open for investigation. So it's a very nice topic which connects linear algebra, graph theory, and chemistry. This is where the subject stands. Okay. I will just try to give you a
a brief survey of whatever has come so far and nullity of a graph. So, thank you very much.
Any questions from the participant?
Are there any questions?
Professor Armugam, sir. I am not with any question, but it is a very interesting thing that I like to focus in, and I'll be in touch with you regarding this particular motion.
Thank you.
Anybody else? Raksha, anybody from audience have a question? Just a
Are there any questions?
Balaji has a question.
Oh, it's not a question.
Oh, okay.
So the way how we taught is excellent, sir. So he is very patient. So although, but I want to see the slide. So is it is it problem for everyone or for only for me? I don't know. So I can't see the slides.
Last 5 minutes, the slide was missing.
The slide I can't see.
Last 5 minutes, it was missing. The slide was missing.
But
Last 5 minutes of the lecture.
but others can see it.
Yes, we could see.
Sir, I can't see. I think there's some problem from my side.
Even Professor Armugam was not seeing it.
Only for last 5 minutes, it was a problem.
Sorry, sir. I think I have some problem in my computer.
Yeah, here also it was all right, I think.
Sir?
Here it was all right. I'm not in the room.
Okay.
But I could see.
Okay. Okay, sir. That's all.
I will explore what exactly the problem is. Okay, some other time, I don't know, when we explore, I don't know how the schedule permits, we will replay this once again some other time. We will see, maybe during lunch break or some time. Okay. Raksha.
Hello? Yes, sir. Yes. I think there was no problem in playing the slides. Maybe there was some network issue at sir's place. Okay, sir. Thank you, Professor Arumugam, for a wonderful lecture. Pradeep, sir, please take over.
Okay, thank you, sir. Thank you, Armugam, sir, giving a wonderful lecture on the validity of the graph and its characterization. Thank you, sir. Thank you so much. Now let us welcome Dr. Balaji Ramamurthy, Indian Institute of Technology, Madras, Chennai. He is giving a talk about generalized Euclidean distance matrices. Welcome you, sir. And over to Dr. Balaji.
Thank you. Thanks, Professor Pradeep. I heard some. Okay, already it's recorded. Okay, thank you.
Raksha, before playing, let him finish talking.
Sir, thank you. Yeah. Thank you. Please play the slides, sir. Thank you. Thank you very much.
Okay, thank you.
So, anyway, this is a talk about generalized Euclidean
Euclidean distance matrices. Euclidean distance matrices are somehow a well-known topic, and our aim is to go beyond Euclidean distance matrices and see what happens. So Euclidean distance matrices are basically symmetric matrices, and they have non-negative. All the entries are non-negative, and we have many interesting properties in there. Whereas the matrices that we are going to introduce, which are called generalized Euclidean distance matrices, they resemble like Euclidean distance matrices, but the most important thing is that these matrices are not symmetric. But still, we can use spectral theorem. We can circumvent the spectral theorem arguments in many of the results. Then we can get the same property as Euclidean distance matrices. So the aim of this talk is to present some results on generalized Euclidean distance matrices. So first, let me introduce generalized Euclidean distance matrices. So before that, first introduction about Euclidean distance matrix. So first you take some n points in Rk. Okay, Rk is the Euclidean space with the dimension k. Suppose you fix n points, x1, x2, xn, then I define a number dij as like this, norm of xi minus xj whole square. Okay, so the distance between xi and xj, square distance between xi and xj is the number dij. Now I will construct a matrix D into dij. So it's an n by n matrix. Of course, all the diagonal elements are going to be 0, and D is a symmetric matrix. D is a symmetric matrix. So we shall say that D is a Euclidean distance matrix. So the meaning for Euclidean distance matrix is that you say that some matrix is a Euclidean distance matrix if and only if Dij can be represented as norm of xi minus xj whole square in some Rk. In some Rk. So this is the meaning of a Euclidean distance matrix. So just let me make some adjustment, some technicalities in this. See, let me put Fij as the inner product between xi and xj. Inner product between xi and xj in Rk is usual inner product xi dot product xj, standard inner product. So now Dij, okay, Dij, if you expand the norm of xi minus xj, the whole square, this is going to be norm of xi whole square plus norm of xj square minus 2 times inner product xi xj. Okay, so 2 times inner product xi xj is nothing but 2 times Fij, and the norm of xi square is going to be Fii, norm of xj square is going to be Fjj. Okay, so Dij can be very neatly written Fij plus Fjj minus 2 times Fij. Okay, so matrices of the form inner product xi and xj are called the graph matrices, and the graph matrices I need not introduce anything. So matrices of this form, they are called graph matrices. So every entry can be written as inner product between xi and xj. Okay, for some vector xi and xj in inner product space. So those matrices are called graph matrices, and all positive semiconductor matrices are graph matrices. They have a very nice representation. So positive PSD matrices are graph matrices, and every graph matrix is a PSD matrix. It is also a well-known result in the theory of positive semiconductor matrices. So Dij is a EDM. Okay, EDM means Euclidean distance matrix. Okay, if and only if there exists a PSD matrix F such that Dij equal to Fij plus Fj minus 2 times Fj. So this is the conclusion that if I use the word graph matrix, if I use graph matrices. Okay, so corresponding to a PSD matrix, you always generate a EDM. Okay, so that's the point that I want to emphasize here. Now, let me make a small adjustment here. Okay, let me make so just to make a smaller, not adjustment, observation here. So first, let me put. So let me introduce this notation. One vector, it's a very useful notation. One vector is a vector of all ones in the space Rn, and J is a matrix of all ones. So it's a random matrix given by 1 into 1 prime. Okay. So matrix of all ones. Now you take X as a diagonal of F. Okay, diagonal of F. So which is x1, x2 up to xn. Okay. Then if you see this Dij carefully, okay, it can be D can be written as D D can be written as x times 1 prime plus this fjj, because of the second term, I can write it as 1 times x prime, okay, minus 2 times f. So this is the in terms of matrix equation, if you write, then it becomes d equal to x is 1 prime plus 1 into x prime minus 2 times f. So equivalently, d is EDM. If only there exists a PSG matrix F such that d equal to diagonal of f into j plus j into diagonal of f minus 2 times f. So I have done nothing here. See, I have done nothing except that I have written it in terms of a matrix equation. This equation dij equal to fij plus jj minus 2 fij, I have translated into a matrix equation. That's all, nothing more than that. So let me do some more thing here. So just let me call this matrix P. Let me call this matrix I minus j by n. Okay, j comes from here, 1 1 prime. I minus j 1 j by n as P. Okay. So of course P is a projection, orthogonal projection in fact. So P is an idempotent matrix. Okay, so idempotent means P square equal to P. And of course, P into 1 is 0. P acting on one vector will always give you the 0 vector, because P times 1 is identity times 1 minus j times 1 divided by n. So that will give you 1. So 1 minus 1 will give you 0. So P times 1 vector is 0. So if you compute P into j, it will be a matrix 0. It's a 0 matrix. P into j is a 0 matrix, and of course, j into P is also a 0 matrix. So if you compute PDP, okay, if you compute PDP, say post multiplied by P and then pre multiplied by P. So the first two terms will not matter here, because j into P will give you 0, P into j is going to give you 0. So PDP will result ultimately in minus 2 times FP. Okay. So given an n by matrix A, so let me call cofactor of A. Okay, let me construct a matrix cofactor of A, which is also an n by matrix. This cofactor COF of A is nothing but it's a new matrix where Aij is replaced with its cofactor. Okay. See, for example, if you take the A11, then you delete the first column and then the first row and then compute the determinant. So that will be the first entry in the cofactor of A. If you compute the 1, 2 entry, delete the first row and then the second column, and then take minus 1 times the determinant. Okay. So this will be the A12. Sorry, this will be not A12. This will be the first 1, 2 entry of cofactor of A. So this is the cofactor matrix. Okay, cofactor matrix of A. Cofactor. So let me denote cofactor sum of A as the sum of all the entries in cofactor matrix of A. So you have given you have 3 items now. You are given an A matrix A, and then you construct a new matrix named the cofactor matrix, and then you have the cofactor sum of A, which is a number. Okay, that gives you the sum of all the entries in the cofactor matrix of A. So this is the following. This is an exercise in maybe linear algebra determinants. So suppose you take any subset of n. Okay, 1 to the square bracket n means 1 to n. If A is an n by matrix, let A of omega denote the principal submatrix formed by deleting rows and columns to index by the set omega. Okay, then you can show that cofactor sum of A of omega is same as cofactor sum of PAP of omega. So this is a very remarkable thing. So it says that the cofactor sum is invariant. Okay, covariant if you multiply by PAP. So this multiply by PAP always doesn't affect anything, and it works for any principal submatrix. Okay, not only any principal submatrix, it works for any square matrix. Okay, so first you can prove it for a principal submatrix, and for our purpose, principal submatrix is also everything. Okay, so this is a very nice exercise. So let me choose omega as I, j. Okay, there are only 2 elements, I and j comes from 1 to n. So PDP is minus 2 times FP, and PFP already noted. So cofactor sum of PDP of omega is same as cofactor sum of D of omega. Okay, because this P is infinity here. So cofactor sum of D of omega is cofactor sum of minus 2 times f of omega. Okay, all I need is only this equation PDP equal to minus 2 PFP, and this is same as cofactor sum of minus 2 times PFP of omega. Okay, so all these are valid now. So okay, Okay, now let me write down the cofactor matrix of D of omega. Okay, remember that omega is I comma j, so D of omega is a 2 by 2 matrix. Okay, D of omega is a 2 by 2 matrix, and it's given by 0, Dij, Bij, 0. So its cofactor matrix of D of omega is 0 minus Dij minus Bij 0. Okay, and the cofactor, if you compute the cofactor sum, it's the sum of all the entries in this matrix. So it is going to give you minus 2 times Dij. Okay, it's going to give you minus 2 times Dij. Put L equal to P of P. Okay, now I am calling this matrix P of P as L for simplification. So minus 2 times cofactor sum of L of omega is going to be minus 2 times Lij plus Ljj minus 2 Lij. Okay, this one cofactor sum of L of omega is simply Li plus Ljj minus 2 Lj. So if you simplify, you get Dij equal to Lij plus Ljj minus 2 times Lij. See, earlier I had Dij as Fij plus Ljj minus 2 times Fij, but now that I have reduced this to Dij equal to Lij plus Ljj minus 2 times Lij, this matrix L has some advantage. L satisfies this property. L times 1 is 0. That means row sums of L is 0, all the row sums of L are zeros, and L is symmetric, so all the column sums are also 0. Okay? And L is a positive semi-definite matrix because L is P of P, and F is PSD, so P times F times P should be again a PSD matrix. Thus, D is a equally distance matrix if and only there exists a matrix L such that row sums and column sums are 0 and Dij calculated as Lij plus Ljj minus 2 times Lij. Okay. So D is a Euclidean matrix if and only if there exists a positive semi-definite matrix L such that Dij equal to Li plus Ljj minus 2 Lij, where L has the special property L times 1 is 0. Okay, and of course if you want to write L equal to Lij in bracket. Okay, so the ij entry of L is small Lij. Please note that. So most of the interesting properties of the EDMs depend on this characterization. So that's what we observe. So based on this observation, we presently we now give a simple generalization of this Euclidean distance matrix. So we say that matrix D is a generalized Euclidean distance matrix if Dij can be written as A square times Lii plus B square times Ljj minus 2ab times Lij. Okay. So see earlier I had only the A as 1 and B as 1. Okay. Now let me introduce two numbers here: A square plus A square Lij plus B square Ljj minus 2ab times Lij. So if you write the principal submatrix as Lij, Ljj, and then the off-diagonal entries as Lij, then Dij is a quadratic form A comma B inner product the 2 by 2 submatrix into A comma B. Okay. So this is the way how we generalize this Euclidean distance matrix. Now L is a okay. Now let me put a very important condition. L is a PSD matrix so that all the row sums are going to be zeros. Okay. So whenever A not equal to B, then a generalized EDM is not symmetric, of course. Okay, because the transpose of D is going to be B square times Lij plus A square times Ljj minus 2ab times Lij. Okay, so this is the way how I am going to get the D transpose. So generalized, so as long as A is not equal to B, this D is not going to be a symmetric matrix. And GDMs are not equal matrices. That's very clear because this is nothing but the this is a this right hand side is a quadratic form of the principal submatrix Lij, Ljj, and then the off-diagonal entries as Lij. Okay, which is a principal submatrix of a positive semi-definite matrix. So which is once again positive semi-definite. So its quadratic form is also positive semi-definite. Okay, so Dij is going to be non-negative matrix. And see, for example, this is the way how I generate a generalized Euclidean distance matrix. I take a matrix L 3 minus 1 minus 2 minus 1 3 minus 2 minus 2 minus 2 4, and you can see that the row sums are going to be zeros. Okay, and of course L is a symmetric matrix, and L is a positive semi-definite matrix. Okay, L is a positive semi-definite matrix that you can prove it easily if you take the principal minus. Okay, if you take the principal minus, they are going to be non-negative. So in that way, you can show that it's a positive semi-definite matrix very easily. So now you take A equal to 1 and B equal to 3. Okay, now I generate a generalized distance matrix Dij equal to Li plus 9 times Ljj minus 6 times Lij. For example, the first entry is going to be 3 plus 9 times 3, 27. Okay, so 27 plus 3, 30. 30 minus, I think, 3 plus 9 plus 6 times Lij. I think I will just check the calculation. I might have made a mistake here. So 3 plus 9 is 3, 27. 27 plus 3, 30. 30 minus 6, it comes out to be 24. Not this one. Well, just check this one. No, I'm sorry. See, L11 plus 9 times L11. So 3 plus 9 to 3, 27. 27 minus 6 to 3, 80. 27 minus 80 is, once again, 3 plus 9 to 3, 27. 27 minus 80 is 9. It should be 9. Okay. Just check this one here. This entry should be 9. So if you take this entry, maybe I have calculated it properly. So this D I have written it properly. Okay. In fact, it's wrong here. So it's not a symmetric matrix. See, A equal to 1 and B equal to 3. This D I have written it wrongly. Okay. So this is not a correct matrix. If you compute this Li plus 9 times Lj, 9 times Ljj minus 6 times Lij, it comes out to be some other matrix. It's not a, this D is not correct. Please rectify. I'm sorry for this. So D will be a non-symmetric matrix in fact. Okay. Okay, so now let me pass on to the results that we have got on generalized EDMs. Okay, first let me tell you that EDMs are very symmetric. Okay, EDMs are any Euclidean distance matrix are symmetric, so all eigenvalues are real, and we know that any Euclidean distance matrix has exactly one positive eigenvalue. It has exactly one positive eigenvalue, and the remaining eigenvalues are going to be either non-negative, either they are 0 or it's going to be negative. So all the remaining eigenvalues are going to be non-positive. This happens for any Euclidean distance matrix, but the GDs are not symmetric. The GDs are not symmetric. In spite of this, we found that all the eigenvalues of a generalized distance matrix are real. In fact, we have shown the following results. Let the D be a generalized distance matrix. Okay? Let the D be a generalized distance matrix. Then D is similar to a symmetric matrix. D is always symmetric to a similar matrix that has exactly one positive eigenvalue. Okay, this has exactly one positive eigenvalue. So the eigenvalues of D are always going to be real, and in fact, it has exactly one positive eigenvalue. So this is a result that motivated. This is the first result that we got on generalized distance matrices. So motivated by this result, we obtained a sequence of results so that I will be doing here. But this is a very striking result. Even though they are not symmetric, we can always show that it has only real eigenvalues. Okay. So the whole result does not hold. See, the significance of this result is that in the generalized Euclidean distance matrix, we assume that the matrix, the positive semi-definite matrix, which gives rise to this GDM, okay, has the property that L acting on 1 is 0. That is, all the quotients are 0. If we remove this assumption, L1 is 0, then we no longer this result is true. If no longer this result is true, in fact, you can show that you can find many examples. In many examples, we found that though if we do not assume that L1 is 0, then the matrix will have complex eigenvalues. This gives all the eigenvalues need not be real. So some of the eigenvalues, if you compute in MATLAB, it gives you complex eigenvalues. So this assumption, L acting on 1, plays a very crucial role to get this result. Okay, to get this result. And of course, we can prove, we can go something more beyond this one. All the eigenvalues of the border matrix D1 vector, you border this matrix using the vector 1, then D1 prime is 0 or real, and also it has exactly one positive value. So this result is somewhat easy. You can extend it very easily. And now we will proceed on to some other result. If A is EDM, then we know that 1 is always the half space of A. Okay, Okay, and 1 is always the common space of A. And if you sum all the entries in the Booth Penrose inverse of A, okay, this is A, I'm sorry, I have written as D. If you sum all the entries in Booth Penrose inverse of A, it will be a non-negative number. It's a very, what I can say, it's a very significant property of Euclidean distance matrices. You sum all the properties in the Booth Penrose inverse of a Euclidean distance matrix, it gives you a non-negative number. Okay, and always one vector is in the column space of A. So we used some new techniques and found that any GDM also has this property. So in fact, we have the following results. Let D be a generalized distance matrix. Then for any generalized inverse, we have 1 prime D minus 1. Okay, D minus D minus is a generalized inverse. Okay, it's not Booth Penrose inverse. You can just take any generalized inverse. So 1 prime D minus 1 remains invariant. So that means that you substitute any D minus here. Okay? You substitute any generalized inverse here, and if you compute this sum of all the entries, okay, that it's a constant. Okay? It remains invariant, and in particular, 1 prime D plus 1, we have shown that it is a non-negative number. Okay? So for any G generalized inverse also it's a non-negative number. Of course, it's the same number. One sum of all the entries in generalized Euclidean distance matrix is also a non-negative number. So that's the theorem that we got. So about the null space of the GDM, so we have proved the following thing. So the null space of a GDM and null space of this EDM they are equal. So diagonal of L into J plus J into diagonal of L minus 2 times L. This is a Euclidean distance matrix. Okay. So the null space of these two matrices are equal. So this gives you that 1 is always in the column space of GDM. Okay. So if you take any generalized Euclidean distance matrix, since the null space of EDM and null space of D they are equal, we obtain this one. 1 is in the column space of D. Okay. So we also found the following result. Suppose the D is a generalized distance matrix, then minus PD plus P. Okay, minus PD plus P is always a positive semi-definite matrix. Okay, and also, in fact, it's a symmetric matrix. That's a little bit difficult to do. PD plus into P is always a symmetric matrix. First of all, it should be symmetric, and normally symmetric, we have shown that it's a positive symmetric matrix. Okay, so even proving that it's a symmetric matrix requires some sort of argument, but still we could prove it. And also, D Booth Penrose inverse of D is negative semi-definite on the subspace 1 per. Okay. So this means that whenever you take a vector which is perpendicular to 1, then suppose you take any vector x which is perpendicular to 1, then x prime d plus x. Okay, the quadratic form x prime d plus x is less than or equal to 0. That's the meaning for this. Okay. So this is the result that we have got. And whenever 1 prime d equals 1 is a positive number, we have a formula to compute the Booth Penrose inverse of D. Okay, the Booth Penrose inverse of D, it says that it is minus 1 over 2ab times the Booth Penrose inverse of the L plus 1 by 1 prime d plus 1. Okay, 1 prime d plus 1. So in fact, 1 prime I have written 1 prime d plus 1 prime d plus 1. Into d plus 1 into 1 prime to d plus. Okay, so this is a formula that this is a more general formula than for okay. Whenever d is a Euclidean distance matrix, already we know the formula, but here we have this term, one term extra, a into b. Okay, a into b, and using this formula, you can also get the Lower's or Graham-Lower's formula for the distance matrix of a tree and so on, but I don't want to do the graph here. So anyway, this is a more general formula. It's a formula here. So this is the result. This is the inverse formula that we got, and I would say that the technique in proving this formula almost resembles the formula for obtaining way how you need it for Euclidean distance matrix. So I won't say that it's anything new, but again, the formula is somewhat, we have to little bit go through some of the details. See, technically, but technically, I would say that we didn't face any much difficulty in proving this result. Okay. And we also obtained some major results, and if you have a symmetric matrix, a very remarkable theorem due to Schur, it says that a diagonal of a symmetric matrix is measured by the eigenvector, the eigenvalue map of D of a symmetric matrix. So lambda of D denotes the just write the eigenvalues of D. Okay, lambda 1, lambda 2, lambda n, and then you write a vector in Rn like this, lambda 1, lambda 2, lambda n. So Schur's result says that diagonal of a symmetric matrix is measured by the eigenvalues of D. Okay, eigenvalues of the symmetric matrix. But here we have a non-symmetric matrix. Still, we get a theorem which is resembles like a Schur's theorem. Diagonal of D is measured by lambda of D, and also we have this result lambda of D is always measured by 1 by 2 times lambda of D plus D prime. Okay, lambda of D plus D prime. And note that lambda of D, they are all vector in Rn, okay, because all the eigenvalues of D are going to be real. So already we proved this result. So because of this, we got these two major results. And now let me finish the talk by giving a small application of these GDMs. Okay, GDMs. So suppose, okay, now just let me define what is called an infinitely divisible matrix. Suppose you take a non-negative matrix. Non-negative matrix means all the entries in the matrix are going to be non-negative real numbers. Okay, that's the meaning for non-negative matrix. We say that A is an infinitely divisible matrix if you consider this matrix A hat mod R. So A hat mod R means every entry you raise it to the power R. Okay, R is a real number which is positive. R is a real number which is positive. So Aij or R is positive definite for every R greater than 0. So this is called an infinitely divisible matrix. So such type of matrices are always interesting in probability theory in constructing infinitely divisible distributions. Okay. So okay. See, for example, okay, you may ask me there are other infinitely divisible matrices. So of course I am giving you some example here. Suppose you take A like this, min of I comma j. You construct an n by n matrix like this. The ij entry is going to be minimum of I and j. So, for example, if you consider the 3 by 3 matrix, it is going to be 1, 1, 1, then 1, 2, 2, and then 2, 3, 3. Sorry, 2, 2, 3. Okay, so 2, 2, 3. This is the min of I comma j for a 3 by 3 matrix. Okay, so ij entry is going to be minimum of I and j. So that's the way how I am going to define this matrix. You can show that this A is an infinitely divisible matrix. If you take A equal to 1 by I plus j, you can show that it's an infinitely divisible matrix. And these kind of matrices are, of course, there are many examples of infinitely divisible matrices. And the question is how to find more examples of infinitely divisible matrices. Because these kind of matrices gives you some sort of probability, infinitely divisible distributions. Okay. So, how to find more examples of infinitely divisible matrices? So, using GDMs, we try to construct infinitely divisible matrices. So, we got this result. Suppose the D is a GDM, then 1 by maximum of Dij and Dji is an infinitely divisible matrix. Okay, so this is the result that we got. Using a GDM, we can get a infinitely divisible matrix like this. The following result, okay, how we prove this result? Just let me explain you it shortly. So the following result is how to use in getting an infinitely divisible matrix. Suppose you take a symmetric matrix where all the entries are going to be positive. Okay, where all the entries are going to be positive. Then you construct a new matrix like this. You take the reciprocal of this one by A and J. Okay, you construct a new matrix like this, reciprocal of each entry. And if it happens that A has exactly one positive eigenvalue, then I can surely say that 1 by A and J is an infinitely divisible matrix. Okay? This is a known theorem. So we used this theorem to prove our theorem on infinitely divisible matrices. So how we have shown is the following. So if we can show that maximum of Dij and Dji has exactly one positive eigenvalue, then we are done. Because this matrix is a symmetric matrix and all the entries are going to be positive. So our job is to finish the proof of theorem. We just need to show that this matrix has exactly one positive value. But the maximum of alpha comma beta is always half times alpha plus beta plus mod plus alpha minus beta. Okay? if you take any two positive numbers alpha and beta, this identity is always valid. So if you apply this identity, you can show that D is sum of these two matrices. First term is half times D plus D prime, and second term is a matrix whose ij entry is Dij minus Dji. Okay. So if you take the first term, D plus D prime is always negative referent on one per. Okay. So this is very easy from the definition of generalized distance matrix. And if you look at this term, second term, modulus of Dij minus Dji, so this is going to be, once again use this identity, A plus B minus 2 times min of A comma B. Mod A minus B is mod A plus B minus 2 times min of A comma B, where A comma B is a positive or positive numbers. So mod Dij minus Dji, so here I have used the notation S, okay, instead of L. L is a ij entry of the matrix which generates DD. Okay. So now instead of L, I have used S here. So mod Dij minus Dij is going to be modulus of A square minus B square into SIA plus SJJ minus 2 times minimum of SIA and SJJ. Okay, so in terms of matrices, if you take the matrix where each entry is modulus of Dj minus Dji, this is going to be Sj plus Js minus 2 times min of SIA SJJ. Okay, just to leave this positive term, it's not going to affect you anything. Okay, in fact, I should have written this positive term, but it doesn't matter. It doesn't matter in proving this result. And this matrix has okay, min of SIA comma SJJ is always positive semi-definite. Okay, it's always positive semi-definite. So if you take any vector which is perpendicular to one, say for example x, okay, then x prime Sj plus Js minus 2 times min of Si comma Sij into J x is always negative. Okay, it's always less than or equal to 0. So this matrix modulus of Dij minus Dji is negative definite on 1 per. Okay, this is negative definite on 1 per, and already I told you that D plus D prime is negative definite on 1 per. So D will be negative definite on 1 per. So D is so maximum of Dij or Dji is a symmetric matrix. It is negative definite on 1 per. So if you apply either Fisher minimax theorem or interlacing theorem, then you conclude that it has exactly one positive eigenvalue. Cannot have more than in fact it should have n minus 1 negative eigenvalues. It's a negative definite on 1 per. So by either the Fisher minimax theorem or even use interlacing theorem, it doesn't matter. Okay. So you arrive you conclude that it has exactly one positive eigenvalue. Okay. So by the theorem that I mentioned to you on infinity reducible matrices, it follows that 1 over maximum of Dij comma Dj is an infinity reducible matrix. Okay. So this is one way how you can construct infinity reducible matrices. So this is a simple application of what we have done as a generalized distance matrices. And in fact, it may be possible that we can prove some more results also. And, anyway, these are the results, and we can see our paper. Balaji, Bhagat, myself, and then Bhagat and Shivani, we generalized distance matrices. It will be appearing in linear material. So this is the thing that I want to present. Thank you.
Professor Pradeep, sir.
Yes. Any questions from the participants?
Yes, participants.
I don't think there is any question from the participants. Thank you very much for giving a wonderful lecture on generalized Euclidean distance matrices. Thank you, sir.
Thank you, Professor Balaji and Professor Arumugam for delivering the talk. I also thank Professor Pradeep G. Bhatt for chairing this session. Thank you, everyone. Session will start exactly at 12:10 IST.
Manjunath, can you see me?
Professor Shivkumar, sir is not here right now.
I see. Okay, fine. You can
Sorry, sir, I couldn't hear you.
you can just let him know that
Okay, sir. everyone. Welcome back, everyone. So we are in the last session of morning session. So in this session we have with us Professor N. Ekamaram, former DDG, CSO Government of India. He worked as a lecturer in statistics at Annamalai. After that, he joined the Indian Statistical Service and retired from the service as Deputy Director General. He worked in the Union Ministries of Agriculture, Industry and Statistics. In the recent past, he served as a guest faculty in the Department of Mathematics at IIT Madras, Chennai, and presently teaching mathematical finance at IIT Tirupati, India. He has sustained interest in research in generalized inverses of matrices and its applications. Today he will be delivering a talk on characterization of Q matrices in linear complementarity problem. Another speaker of this session is Professor Debajit Kalita. He received PhD degree from IIT Guwahati. He has published many papers in the areas of graph theory. Presently, he is working as an assistant professor in the Department of Mathematical Sciences, Tezpur University. His topic of interest are algebraic graph theory, linear algebra and its applications to graph theory, adjacency and Laplacian spectra of graphs. I welcome both of you. I now request Professor Vasudeva Guddaku from Mahi Manipal to chair this session. Over to you, sir.
Thank you, Raksha. So now I request Dr. Ekamaran to talk on characterization of Q matrices in linear complementarity problem.
So, Ekamaran, you want to say a few words before we start? Okay, with the permission of chairperson, we will play the recording then.
On characterization of Q matrices in linear complementarity problem. We are going to cover the following aspects. One is the linear complementarity problem, which in short is denoted as LCP-MQ. There are two parameters M and Q in LCP. A Q matrix is one which gives solution to all Q in the LCP. That is, the matrix M is a Q matrix if LCP MQ has solution for all Q. Then we will introduce what is called the border matrix algorithm. And then finally, we will give some necessary conditions that we have obtained for a matrix M to be a Q matrix using the border matrix algorithm. Linear complementarity problem LCP-MQ is to find solution WZ to the following equations. That is, W minus MZ is equal to Q, WZ is greater than or equal to 0, Z transpose T, W is equal to 0. Alternatively, these equations can be written as mz plus q is greater than or equal to 0, z is greater than or equal to 0. Z transpose mz plus q is equal to 0. Now let us concentrate on Q matrices. M belongs to the class Q, that is the set of all Q matrices, if LCP MQ has a solution for all Q. In fact, in LCP, there are two fundamental issues. That is, to find a solution to LCP if it exists. And then what are the Q matrices? So these are the basic issues. But research has gone into other aspects, so many other aspects. But the basic issue still remains to be tackled in full. Now let us see some definitions. M is said to be in the class P if all its principal minors are positive. And this class P, if M belongs to this class P, M is a Q matrix. And a P matrix gives a unique solution to LCP for all Q. Closer to P, the class P is the class P naught. If M is in P naught, all the principal minors of M are non-negative. But a P naught matrix may not be a Q matrix. Conditions for a P naught matrix to be a Q matrix have been found out. There are some reasons. The another class of matrices is called E naught F matrix, that is fully semi-monotone matrix. A matrix M belonging to E naught F, if it belongs to E naught F, if LCP MQ has a solution WZ with exactly n components positive. If such a solution is there, that solution is unique. This P naught is similar in its solution uniqueness as E naught F. And P naught is contained in E naught F. A question was raised by Band long back, maybe 30 years ago. What are the conditions required by E naught F so that E naught F, if it belongs to Q, it will be a P naught matrix. Because E naught F and P naught have similar properties. E naught F is a bigger class, but now Band's question is, if E naught F is to become a Q matrix, what is the condition to be satisfied by that matrix, E naught F matrix? So these are the questions which spring from the fundamental property of the P matrix. Now, what we are going to do in this session, we will try to characterize the Q. We will attempt to characterize the Q by using what is called border matrix algorithm. This is a term now we are introducing. Now, MKS algorithm provides a set of solutions to the points on a straight line, to all the points Q on a straight line, and the solution varies as a continuous function of the points on the line. That is, the algorithm traces a straight line, and for each point on the straight line, the algorithm provides a solution to the LCP for that particular point, Q. So we make use of the continuity property of the solution Z. When the algorithm traces this line, and we propose a variant of Lemke's algorithm called the border matrix algorithm. And using this border matrix algorithm, you obtain some necessary conditions for a matrix M to be a Q matrix. Now let us see the LCP as such. The LCP equations can be represented as in a different format. That is putting the variables W1, W2, etc. W at the top of the matrix I, and Z1, Z2, etc. Zn at the top of the matrix minus M. Now, because of the complementarity property, if W1 is in the solution, takes part in the solution, Z1 will not take part. So, in general, if Wi is there, Zi will not be there in the solution, and vice versa. Therefore, the jth column of I and the jth column of minus M are called complementary vectors. And in any solution, we require only one vector from a pair of complementary vectors, and there are n pairs of complementary vectors, and from each pair we select one and constitute a matrix C. And if the equation Cx is equal to Q has a solution with x greater than or equal to 0, we have obtained the solution for the LCP. And there are 2 power n such complementary matrices C. Therefore, it is very difficult to exhaust all these complementary codes and search out the solution for Cx is equal to Q. Now let us see what is the complementary code. The complementary code boss C is the set of all Cx, x greater than or equal to 0. And boss C is called a full cone if C is not singular. The cone boss C is strongly degenerate or an absorbing cone if Cx is equal to 0 for x greater than or equal to 0 and x not equal to 0. And boss C is a weakly degenerate cone if Cx is equal to 0 and boss C is not an absorbing cone. Boss C is a reflecting cone. This term I am introducing in the context of Lemke's algorithm as a cone that intersects with the positive orthet. Now let us see diagrammatically what are these full cones, reflective cones, and absorbing cones. In the example 1 here, the column vectors minus m.1 and minus m.2 are drawn here, and the cones are complementary cones are the first orthent constituted by I.1 and I.2, the other cone constituted by minus m.1 and I.2, the third one is minus m.1 and minus m.2, and the fourth one minus m.2 and I.1. Thus we exhaust all the 4 complementary cones. Because the order of the matrix M is 2, there are 2 complementary cones. Now, if you see the complementary cones, each complementary cone has full cone. All the cones are full cones. In the example 2, we have drawn this diagram. Here we have marked all the complementary cones. Here also, all the complementary cones are full. But in the case of Lemke's algorithm, if the algorithm starts from the positive orthant and comes down to and touches I dot 2, then the I dot 1 will go off. The complement of I dot 1 is minus M dot 1. So we will get the next cone constituted by I dot 2 and minus M dot 1. Therefore, after touching this I dot 2, Lemke's algorithm will go back, will be reflected. Therefore, this particular cone is called a reflective cone. In the third example, we have got this positive orthant and the cone constituted by I dot 2 and minus M dot 1. If you apply Lemke's algorithm, it starts from the positive orthant, touches I dot 2, but then when I dot 1 goes off, the complement of I dot 1 is minus M dot 1. Therefore, the cone is again there, so it smoothly descends and touches minus M dot 1. When it touches minus M dot 1, the vector I dot 2 goes off and it is replaced by its complement minus M dot 2. Therefore, you get this cone, which is a straight line, which is not a full cone. This sort of a cone is called an absorbing cone. Now, when we apply Lemke's algorithm, for example, in the case of example 1, the algorithm starts from the positive orthant, and when it is traveling along this line is nothing but, suppose Q is here at the end, and the vector P is here. This line is parallel to the vector P. Therefore, this line is nothing but Q plus theta P for some theta. So this line is defined by Q plus theta P. So as theta varies, the points on the line varies. As theta decreases, the line comes down, the points we descend, we come down. And when theta is equal to 0, we reach the point Q. And Lemke's algorithm for each point on this line gets you a solution, Z. And since we are traveling smoothly along this line, the solution Z of Z is also changing continuously. So Z becomes a continuous function of theta. One can extend this line up to infinity, and therefore we can say take theta is infinity. Theta starts from infinity and descends and comes down and reaches Q. So all along this path, the Z, the solution Z for each point on this line, the solution Z for each Q, the different Qs we are getting on this line, for each Q, whatever Z we have, if you see all these Qs, this Z is a continuous function of theta. Whereas here in example 2, let us consider a similar case. Lemke's algorithm starts from the positive orthant. Suppose it starts from infinity in the positive orthant. For this line, theta is infinity. From infinity, it is the value of theta is decreasing and coming down and touches I dot 2 for value theta is equal to some theta naught. And once it touches, it cannot further go down. So it gets reflected. And when it gets reflected, we get again theta positive and goes to infinity. So in this case, when it is traveling from infinity to this I dot 2, it is traveling in the cone
positive orthant. It is traveling in the positive orthant, and when it gets reflected, it is traveling in the next cone constituted by I dot 2 and minus m dot 1. Therefore, if you see the solution to the points traversed by this line, for a particular point Q, there will be two solutions. One solution is given by the positive orthant, the other solution is given by the cone I dot 2 minus m dot 1. So there are two theta, one theta, two solutions. Therefore, we cannot consider the solution Z in this case as a function of theta, because for one theta, there are two solutions. Now let us consider the example 3. Here also we start from infinity and smoothly it descends and touches minus m dot 1. When it touches minus m dot 1, the cone absorbing cone takes over, minus m dot 1, minus m dot 2, and this absorbing cone itself gives a solution for 0. If the absorbing cone is C, then there is a solution Cx is equal to 0. Therefore, we can keep on adding that sum alpha x. If the original solution is z0 plus the alpha x, I mean corresponding to that x, there is a z value, say z bar. So z0 plus alpha z bar will be a solution for all alpha greater than or equal to 0. Therefore, we get infinitely many solutions for the point. At this point, we get infinitely many solutions. So, though it has touched this point, theta is here. It has theta has reached 0. If it is q, theta has reached 0. But then we get infinitely many solutions for this point. Now, what we are going to do? We are going to introduce a time index. Apart from this theta, parameter theta, we are going to introduce a time index. Now, in the first example, when the theta is infinity, let us call t is minus infinity, the past, remote past. And then when theta is coming down and touches I dot 2, here t is equal to 0. And when it is coming further down, theta keeps increasing. And when it touches q, the solution is obtained. So now theta itself is a function of t. Theta is a function of t. So now in this case, second example, similarly, from infinity, the t is minus infinity, and it comes down and touches the I dot 2. Here it is t is equal to 0. Then again, when it gets reflected, t is increasing. We don't say t is negative. Keep increasing. T is increasing, and for the particular value here q, in earlier case we have seen for a particular theta there is one particular value, but here the t values are different. When it's traveling in the positive orthant, at this point t has one value, and then after touching it, when it goes back, it is traveling in the next cone. We are increasing t. Is always increasing. Therefore, from 0 it is increasing. So t value will be different. Therefore, theta is a function of t. It's a proper function of t, and the z is a proper function of theta of t. And similarly, here also in the third example, we can have a similar definition of for t. T is starting from minus infinity and comes down, and here t is equal to 0. And at this point, t has some value, say tm. At this tm, there is a z value, and then we keep on increasing t because the z value, the solution is infinite. We can keep on increasing the solution, and accordingly t will also be increasing and it will go to infinity. So here t varies from minus infinity to plus infinity. Theta varies from plus infinity to some value. So that is the situation here. So we are introducing a time parameter t, so that theta is a continuous function of t, and then the solution is that though it depends on theta, for one theta z may be different, but then the z of theta of t is unique. Therefore, this, if we call this z of t is equal to z of theta of t, then z of t is a continuous function of t. This is the concept, the basic concept that we are introducing here. That is, we are showing that z is a continuous function of the time index t. So this is what I have explained in this slide. This Lemke's algorithm LCPMQ is implemented with the auxiliary vector P. This is the auxiliary vector P. Algorithm attains a solution to LCP M Q plus theta P for theta in an interval. Theta here in this, the interval here in the first example is infinity to the particular point, here theta 0, infinity to 0. And here in this case, the theta is varying from theta to here, this at this point, whatever theta naught is there, because afterwards it is not decreasing. So for particular interval of theta, the algorithm obtains a solution for M Q plus theta P. The algorithm starts with a solution for M Q plus theta P, theta naught P, where Q plus theta naught P is on the facet of Rn plus. That is, the theta naught is the point where it touches I dot 2 or I dot 1, whatever the case may be. Here in this case, it touches I dot 2. If the line is here, somewhere here, it will touch I dot 1. So this at this point, whatever the value of theta is, that we say theta naught. The algorithm then passes through the sequence of complementary cones, C0 to C1, etc., until it reaches the point Q. So in the first example, it traverses on this line and passes through the first cone, positive or then second cone, and then the third cone, it touches the point Q. So till it touches the point Q, the algorithm moves from one cone to another, and when it touches the Q, it gets a solution. If it doesn't give solution, it meets with an absorbing cone or a reflecting cone. That we have seen. When there is no solution, suppose the Q lies somewhere here, in the second example, it is not getting a solution, but it is getting reflected. So it meets with a reflecting cone when there is no solution. Or in the third example, the point Q, if it lies here, then it is getting absorbed in this absorbing cone. It cannot reach Q. So in this case also, it is not giving any solution. So either it gives solution or it meets with an absorbing cone or reflecting cone. So now I have explained what is the time index t that is given here. So Z of t is a continuous function of t. And the time parameter t, index t, varies from minus infinity to some particular number tm or minus infinity to plus infinity. So this is how we introduce the time index and show that Z is a continuous function of t. Now, when t tends to infinity, in any case, when t tends to infinity, whether it meets with the algorithm, meets with the absorbing cone or reflecting cone, the modulus of Z of t will go to infinity. Some component will go to infinity. Now, this property of continuity of the solution was exploited in a paper by Mohan, which was published in Meta-4. Now, let us introduce what is what we may call bordered matrix algorithm. Consider the border matrix M. B, V, U transpose B. And you take the vector Q, Q1, and the last component is Qn. Q1 has n minus 1 components, and the last component is Qn. Now, apply Lemke's algorithm to the LCP BQ1 with auxiliary vector V. Now, assume that V lies in the interior of a complementary cone pos C0. Now, so far we have seen that the Lemke's algorithm starts from the pos. Also start the algorithm from any full cone with an auxiliary vector V lying in that full cone. So that we can do once we know, if we know a particular cone, which is a full cone, and you take a vector V as auxiliary vector lying in that full cone, we can start the Lemke's algorithm. Now in this case, suppose that there is full cone and V lies in that full cone. This assumption, we'll see how this assumption is satisfied later on. So we can implement this Lemke's algorithm. Now, suppose Z of t, now we have already defined what is the time parameter t. With the time parameter also, we are now seeing this Lemke's algorithm applied to BQ1. Suppose Z of t is one solution to the LCP. Z of t is a solution to, when I say Z of t, this is the solution because it's a one-to-one function. Z of t is a solution to BQ1 plus theta of t V. Suppose the solution, then Z of t, theta of t is a solution to LCP MQ, where Q is Q1 minus U transpose Z of t minus B. How? Now, this Z of t is a solution to the first problem with B as the matrix, B matrix. Then W1 of t for this first LCP, W1 of t with the n minus 1 components minus B times Z of t is equal to Q1 plus theta of t V, which I can write as W1 of t minus BV Z of t theta of t is equal to Q1. Then let me say Wn, this Wn will be 0 minus U transpose B Z of t theta of t, you call it Qn of t. So this Q1 of t is nothing but this part. So for each solution Z of t with respect to the algorithm applied to the matrix B, we get Qn of t. So Q1 is fixed. So when the algorithm for B is taking place, when it is working, the Q1 remains the same. Q1 remains the same and the Q1 of t varies. Now, if Q1 of t, which we are getting in this process, if Q1 of t takes all values, real values, then M is a Q matrix, finished. For each Q1, arbitrary Q1, when you apply this algorithm to the matrix B, Lemke's algorithm, and in the process, whatever Q1 of t we are getting, if Q1 of t takes all real values, then the matrix M is a Q matrix. So this is the idea behind investigating the property, Q property of a matrix. Now the range of t, we have seen it is minus infinity to Tm, particular value. Tm can be plus infinity. So in this range, if Qn of t takes all real values, then the matrix is a Q matrix. Now this is the algorithm, border matrix algorithm. We are using Lemke's algorithm, we are using it for the subproblem with the matrix principal submatrix B. And by means of the time index T, we are identifying the Z of T as a continuous variable. And that variable we apply here for the last row and get the last component of the Q, where Q1 is fixed and this Q1 of T varies. And if the Q1 of T takes all real values, then given matrix is M matrix is a Q matrix. And one can further investigate if Q1 of T doesn't take all the values, what will happen? So it is a point for investigation using this border matrix algorithm. Now, what can we say about this border matrix algorithm? Now, if you take this example, M, where B matrix is 1 minus 1 minus 1 1, LCP MQ with the Q minus 1 minus 1 minus 2 is not solvable by Lemke's algorithm, but BMA solves it. However, this matrix M is not a Q matrix. So this one example is to show that BMA solves, but Lemke's algorithm fails. Now let us come to the Q property. Now, one necessary condition we find using this border matrix algorithm is if K of B is equal to set of all Q1 such that LCP BQ1 has a solution. That is, K of B is nothing but the union of all complementary cones constituted by with respect to B. And V should be in the interior of K of B. If M is a Q matrix, V must be in the interior of K of B. That is a necessary condition. That is, in this example, if you see, the 1 minus 1 is V. This should be in the interior of KB, K of B. But you see, this is simply a straight line. And if you write out the geometrically, if you represent, we will see that 1 minus 1 is on the border. It is not in the interior of K of B. This is not on the interior of K of B. The matrix, this one we have already seen in the case of the absorbing cone, example 3, minus m dot 1, minus m dot 2. These two vectors are the vectors of matrix B there, and it is absorbing cone. And then 1 minus 1 is again on the same line. It is not in the interior of K of B. The interior of K of B is the full of space, and this 1 minus 1 is on the border. It is not in the interior. Therefore, this matrix, this matrix M is not a Q matrix. Here we have. This matrix M is not a Q matrix. Whatever the last row may be, this matrix is not a Q matrix. Now let us define what is this Schur complement. Let us say M of J is BJJ, BJ, UJ transpose B, where BJJ is the principal submatrix of B obtained by the index set J. Then it is defined as MJ as B minus UJ transpose BJJ inverse VJ. This is a Schur complement. Let us keep this Schur complement for defining, getting the necessary condition, another necessary condition. This condition is, there exists a J such that BJJ is non-singular. There exists an index set J such that the principal submatrix BJJ is non-singular. The pass of CJ contains B and SMJ is greater than 0. The Schur complement is positive. And the concerned cone is contains V, and the cone is non-degenerate cone. That is, Vjj is non-singular. So this is the next condition. Now, as an example, let us see. Now, in this bordered matrix, if B belongs to E0, it's a E0 matrix, and B is positive, and B is less than 0, B is less than 0, M is not a Q matrix. M is not a Q matrix because pos I, the positive orthant, is the only cone containing the positive vector V. There is no other cone intersecting the positive orthant. Therefore, pos I is the only cone containing a V. And the Schur complement, if you see with respect to that, that is simply V, which is negative. So Schur complement is not positive. Therefore, it is not a Q matrix. Let us see from this, if M is a P matrix, we can put this question. If M is a P matrix, minus M is not a Q matrix. That is because you take any Schur complement SMJ of this P matrix, any Schur complement V SMJ, that will be negative. Therefore, minus M cannot be a Q matrix. Now, one can surmise from the above two properties of Q matrix, we can conclude that for every Q matrix, there exists a principal pivotal transform, PPT, that gives one of the columns non-negative. Here we see that since V is contained in the pos C, then with respect to that C, if you take PPT and check up, we will see that the Schur complement of the last element, will be just as the Schur complement SMJ, and that will be positive. And since V is contained in that C, then when you take PPT, this last column, this instead of V, we will get a non-negative vector. In addition to the above two necessary conditions, we can add one more condition to make the three conditions make a sufficient condition. If C is an absorbing cone with respect to B, C is an absorbing cone, then Cx is equal to 0 for x greater than or equal to 0, and Z0 is a corresponding non-trivial solution to LCP B0, then minus U transpose Z0 minus B should be greater than 0. Or if pos is a reflecting cone, then again similarly, there is X such that Cx is equal to B, because V, the cone, reflecting cone contains V, Cx is equal to V, and then corresponding to that XV there is a Z, let us call it ZR. So minus U transport ZR minus B should be greater than 0. So if one of these conditions are satisfied in addition to the above two conditions, necessary conditions, then it makes the set makes a sufficient condition for the matrix M to be a Q matrix. Now, for example, if you consider this matrix partition, bordered matrix, let B be an E0 matrix, alpha positive, U less than 0, and V positive. In this case, since V is positive, alpha is positive, we can start the algorithm from the positive orthant, and in the Lemke's algorithm applied to B, suppose it cannot have a reflecting cone because it is a E0 matrix. That algorithm cannot have a reflecting cone because it is E0 matrix. And if you beat with the absorbing cone, what happens with that Z0? If you multiply minus U transpose Z, U itself is negative. Therefore, minus U transpose Z will be positive. So we will get the Schur complement. Will be positive. The product will be Qn of T will be positive. Therefore, we will get only positive values, and Therefore, we'll get all values, real values, because we can indefinitely increase, because it is absorbing cone, indefinitely increase Q1 of t. So we'll go to a positive infinity. Minus infinity is always ensured. For Q1 of t, minus infinity is ensured. And from here we see Q1 of t can be arbitrarily large. Therefore, this matrix is a Q matrix. So we have seen in this talk, we have used the continuity property of the solutions to LCP, and we have exploited to characterize Q. And this sort of exploitation using this border matrix algorithm, one can try to see the properties of E naught F, and there is a scope that further properties of this such E naught F can be explored by applying this border matrix algorithm. And the references that you may see for this talk, the materials are from S.R. Mohan, 1990, Mathematics of Operations Research. The paper by M.W. Jeter and W.C. Pai, some remarks on copositive Q matrices and on a conjecture of PAN. Then the paper which gives G.S.R. Murthy and T. Parthasarathy gives extensive results, interesting results, very on E naught F matrices. It was published in some journal. So this is the background that I had for preparing this talk. So with this, I close my talk. Thank you all.
So, thank you, Dr. Ekambaram, for giving a talk on characterization of Q matrices in LCP. Now,
Are you able to hear me?
Yes, sir. Yes, sir. Yes, sir.
Okay,
Yeah.
that's good.
Yeah.
See, actually, this idea of a border matrix algorithm and the continuity property, I revisited in my attempt to solve this Banks conjecture. This Banks conjecture has been occupying the minds of researchers for a long time. Is as well as some 30 years old. And Professor T. Parthasarathy and G.S.R. Murthy, they have done a lot of work to prove Banks conjecture. And I also joined later, though I was not in the academics. Later on, after my retirement, I also attempted to solve that. And in that process, I found that this border matrix algorithm, which I stumbled upon, is a useful tool for exploring further Banks conjecture. So in that process only, just I have proposed this border matrix algorithm. And the continuity property of the solution to LCP, that is not exploited anywhere. That's what I find. So this I made use of, and proposed this border matrix algorithm. And still I hope with the help of this BMA, one can solve the Banks conjecture. And in fact, I have nearly found out the solution. Yes, the Banks conjecture is true for Q matrices. The Banks conjecture is proposed in general for Q naught matrices. A Q naught matrix is not need not be a Q matrix. So Banks conjecture is with respect to Q naught matrix, but I am able to, I think I have solved it. I am able to show that for Q matrices, Banks conjecture is true. Anyhow, apart from this, BMA as such is a good tool to visualize what is happening in the case of Lemke's algorithm, and we can try to explore further properties of Q naught matrices using this algorithm.
Yeah. Thank you, sir. So quickly, we'll have some questions from participants. So any questions to Dr. Ekambaram?
Participants, any questions?
I thank Dr. Ekambaram for the talk. Yeah, thank you, sir. And
thank you.
Yeah.
Thank you.
Now I request Dr. Debajit Kalita to present a talk on algebraic connectivity of graphs constructed with given blocks. Okay, so Dr. Debajit?
Yes, thank you very much.
Yeah, before that, you can speak few words before we start. Yeah.
Yeah, this talk is actually based on our work with my student Kuldeep Sharma. So I thank him, and we are motivated by the work of Bapot Lal and Poti, and I will now request to play the video.
Yeah.
Thank you.
Good afternoon, everyone. First of all, I would like to thank the organizer for inviting me to speak on the title Algebraic Connectivity of Graphs Constructed with Given Blocks. Throughout this talk, suppose that we are given a set of blocks, and with these blocks, we want to construct all possible connected graphs. Then the question is, what can be said about the structure of the graph, minimizing the algebraic connectivity among all such graphs? And it was answered by Bapot, Lal and Poti in around 2011. And here in this talk, we put a restriction on the class of graphs constructed with these blocks. We take the collection of connected graphs constructed with these blocks, keeping the number of pendant blocks fixed. Now, what is a pendant block? A pendant block is a block having exactly one point of articulation. And then we are interested to see the structure of the graphs, minimizing the algebraic connectivity among all such graphs. And in the end of this talk, we will be able to see that structure. So we begin with the definition of adjacency matrix of a graph. Suppose Z is a graph on n vertices, then the adjacency matrix is an n by n matrix with ijth entry aij equal to 1 if the vertices I and j are adjacent, otherwise it is 0. So it is a symmetric matrix. Then the Laplacian matrix of a graph Z is denoted by Lz, and it is defined as dz minus Ag, the adjacency matrix. So where dz is just the diagonal matrix with degrees on the diagonals. So one can easily see that the row sums of Lz are all 0. So 0 is an eigenvalue with the factor of all ones as corresponding eigenfactor. And not only that, this Lz is positive semi-definite. So all its eigenvalues are non-negative. Also, the rank of Lz is exactly equal to n minus k, where k is the number of components of G. So multiplicity of 0 as an eigenvalue is k, if k is the number of components of G. So in particular, if Z is a connected graph, then 0 is a simple eigenvalue of Lz. So that says that the second smallest eigenvalue of Lz is positive if and only if the graph is connected. So the second smallest eigenvalue can be viewed as a quantitative measure of connectivity of the graph. And this was observed by Fiedler. And the second smallest eigenvalue of Lz is popularly known as the algebraic connectivity of the graph Z. And the term algebraic connectivity was first coined by Fiedler. An eigenvector corresponding to the algebraic connectivity of the graph Z is known as a Fiedler vector of Z. Now, this is the work of Bapot, Lal and Poti in around 2011-12, where they have studied the problem of extremizing the algebraic connectivity over all graphs made with some given blocks, with a restriction that the blocks have at most 2 points of articulation. And they call such graph having that restriction as a restricted graph. And in that paper, they have provided a comparison of the algebraic connectivities of the sunflower graphs. This is an example of a restricted graph. One can easily see that the blocks have at the most 2 points of articulations. Now, for a restricted graph, Bapot, Lal and Poti in 2012 in their paper, they have constructed a block structure. Now, how they have constructed a block structure of a graph? Suppose Z is a connected restricted graph with the blocks B1, B2, Bk. Then replace the block Bi by an edge Ei such that Bi1, Bi2, Bir, the blocks, have a common point of articulation if and only if the edges Ei1, Ei2, Eir have a common vertex. And clearly, the resulting graph is a tree, and they have called it block structure of the graph Z. So in particular, any tree is a block structure of itself. Because any tree is a restricted connected graph, and if we see the block structure, we get the tree itself. And we denote the block structure of a graph Z by this symbol throughout this talk. So for example, this is a restricted graph. Its block structure is this graph. And we keep the labels of these points of articulations in the block structure also. This U1 is a point of articulation and it is common to this block, and this block. So we will denote this vertex by this U1 only. Similarly, this vertex by U2, this vertex of this by U3. And these vertices, we can name it by any other symbol. So in 2012, Bapot, Lal and Poti proved that the minimum algebraic connectivity is attained for a graph whose block structure is a path. And from their result, it follows that among all trees on n vertices, the path on n vertices minimizes the algebraic connectivity. And here in this talk, we call a block pendant if it contains exactly 1 point of articulation. And suppose that we are given a collection of blocks and consider the class of all possible connected graphs made with these blocks with the restriction that the number of pendant blocks is fixed. Then the question is, what can be said about the block structure of the graph which minimizes the algebraic connectivity among all such graphs? So before proceeding, we have some notations to be introduced. So by this symbol, we mean the class of all connected graphs made with the given blocks B1, B2, Bk such that R of them are pendant. And suppose Y is a fiddler vector of a connected graph Z, then a block B is said to be positive if YV is positive for all vertex V of the block. Similarly, the block B is said to be negative if YV is negative for all vertex V of the block. Block B is said to be non-negative if YV is non-negative for all the vertices of the block, and so on. Block B is said to be a zero block if YV is zero for all vertex V of the block. And now we give a construction of graphs from two given graphs G and H. This is a very well-known construction. This is very well known in the literature. Suppose U is a vertex of Z and P is a vertex of H. Then by this symbol, we mean the graph obtained from Z and H by identifying U and V and then renaming it as a vertex W. This example will help us to understand that. Suppose Z is a graph and U is a vertex of Z. H is another graph, P is a vertex of H. And we construct this graph by identifying U and V and renaming it as W. Okay. This is a graph. Then this H is known as a branch of this new graph at W, or Z is also known as a branch of this graph at W. And then what does relocating branch mean? Relocating a branch mean? Suppose that we have a graph G1 having a branch H at the vertex U. This is a vertex V. They are alternative name of U's. And suppose I will take this block to this vertex like this. So I get a new graph G2, and this new graph G2 can be obtained from Z by relocating that branch like this. So this is the graph G1. This is the graph G1, which has a branch H at U. We relocate it, we get a new graph Z2 like this. Then the question is, how their algebraic connectivity behaves after relocating a branch. The next result says the effect on algebraic connectivity after relocation. Suppose G1 is a graph having H as a branch at U. And so Z2 is obtained from G1 by relocating the branch H from V1 to V2. G2 is this graph. And say X is a fiddler vector of G1 such that X V2 is bigger than or equal to X V1 and both of them are non-negative. And also if H is non-negative with respect to X, then the algebraic connectivity of this graph Z2 obtained from G1 by relocating H is smaller than or equal to the algebraic connectivity of the original graph G1. And the equality holds if and only if X V1 equal to 0 equals to X V2 and sum of XW equal to 0. The sum is taken over all neighbors W of U, and X is a fiddler vector of G2. Now this lemma says that among all connected graphs in this class, the algebraic connectivity is minimized by a restricted graph H. So that means there is a restricted graph H which will give us minimum algebraic connectivity over all such graphs. Now, what do we mean by a pure path? A path is said to be pure if it contains at most 2 points of articulations of each block. So, for example, suppose this is a graph, then we consider this path, then this path is a pure path. One can see that. Whereas this path is not a pure path because it contains these 3 vertices and 3 of them are points of articulation of a single block. That's why this is not a pure path. Then this is a very well-known theorem called Fiedler's monotonicity theorem. Now, what does this theorem say? If Z is a connected graph and Y is a Fiedler vector of Z, then exactly one of the following 2 cases occur, case A and case B. Now, what does case A say? There is exactly one block B in Z which contains both positively and negatively evaluated vertices with respect to Y. And every other block has either vertices with positive valuation only, that means every other block is either positive or negative or 0 block. And every pure path P which starts at a vertex I of the block B and contains no other vertex of B has the property that the valuations at the points of articulation contained in P form either an increasing or decreasing or a 0 sequence along this path according to whether Y I is positive, negative or equal to 0. And what does case B say? No block of Z contains both positively and negatively evaluated vertices with respect to Y. And in this case, there is exactly one vertex, Z, for which YZ equal to 0, and Z is adjacent to a vertex, some vertex W, for which YW is non-zero. And this vertex Z is a point of articulation of the graph. And each block contains either vertices with positive valuation only, and in that case vertices with or vertices with negative valuation only, or vertices with 0 valuation only. So each other block will be either positive, negative or 0 block. And every pure path P which starts at Z has the property that the valuations at its points of articulation either increase, and then all valuations of vertices on P are positive, or decrease and then all valuations of vertices on P are negative, or all vertices of P are 0. And not only that, every path that contains both positively and negatively evaluated vertices should pass through the vertex Z. And because of this theorem, graphs can be divided into 2 different types of graphs. So type 1 graph and type 2 graph. Now a graph Z is said to be type 1 graph if case B of Fiedler's monotonicity theorem hold, and it is said to be of type 2 graph if case A of Fiedler's monotonicity theorem holds for G. Now this is an example of a type 1 graph, and these are the valuations of a Fiedler vector, and this is that vertex Z for which the valuation is 0 and every other block is either positive or negative, you can see. And then this is a graph, and these are the valuations of a Fiedler vector, and we can see that this is a type 2 graph. And this is a block which contains both positively and negatively evaluated vertices. This edge is a block. And other blocks are either positive or negative. And this block is known as the characteristic block also. So what is a characteristic block? We will see. Characteristic vertex and characteristic edge. What does that mean? Z is a connected graph. Y is a Fiedler vector of Z. A vertex phi is called a characteristic vertex of Z with respect to Y. If YV is 0 and V has a neighbor U such that YU is non-zero. An edge UV of Z is called a characteristic edge of Z if YU times YV is negative. That means YU and YV are of opposite signs. Okay. So for example, this is a characteristic edge. This edge has positive valuations at these end vertices. Opposite valuations. This is positive, this is negative. So this is a characteristic edge. Whereas in that graph, this is a characteristic vertex. Okay. Now that we have already seen that there is a graph which is a restricted graph and it minimizes the algebraic connectivity among all graphs in this class. Then the graph that minimizes the algebraic connectivity may be of type 1 graph. Now if it is a type 1 graph and it is a type 1 graph, then it has unique characteristic vertex phi naught. Okay. Then that vertex phi naught is a point of articulation of the graph Z. So this point of articulation must be in the block structure. And then the degree of this vertex in the block structure is exactly equal to 2. So this gives us a crucial information about the block structure if the minimizing graph is a type 1 graph. And then if the minimizing graph is a type 2 graph, then also we get a crucial information with the help of this lemma. Suppose that Z is a type 2 graph with a Fiedler vector Y and say phi naught is a point of articulation contained in the characteristic block B naught of Z. So then YV naught is non-zero because it is of type 2. So furthermore, if B naught is not pendant and U naught is the other point of articulation contained in B naught, then YU naught times YV naught is negative. That means YU naught and YV naught are of opposite signs. So this is the case when Z is a type 2 graph. Now, if the number of pendant blocks is k, then the block structure of any graph Z here in this class is nothing but a star on k plus 1 vertices. And in this case, the block structure of a graph minimizing the algebraic connectivity is also a star on k plus 1 vertices. And because of that, now onwards we consider R to be less than k. Okay. So suppose that Z is a restricted connected graph that minimizes the algebraic connectivity among all graphs in this class where R is less than k. And say Y is a Fiedler vector of the graph Z. And in case A, suppose Z is a type 1 graph and the unique characteristic vertex is say phi naught. Now since R is less than k, the number of pendant blocks is less than k, so Z has a non-pendant block B containing phi naught. So non-pendant block B means it has more than one point of articulation. And P naught is already a point of articulation, so B will have another point of articulation, say U naught. And we can see that this block B is a non-zero block. So without loss of generality, we can assume B to be non-negative. And so why U naught is positive? And the edge in the block structure of the graph G corresponding to this block B, we will denote it by E plus, and its both end vertices will be U naught and Phi naught. Because P naught is a point of articulation, U naught is a point of articulation, they will be there in the block structure. Okay, and the edge corresponding to this block, we will denote it by E plus, and say it is simply the edge U naught V naught in the block structure. And in case B, if G is a type 2 graph with the unique characteristic block B naught containing a point of articulation V naught, then V naught is non-zero. We can see that. So without loss of generality, we can assume why V naught is negative. And in this case, we use E plus to denote the edge U naught V naught in TBG in the block structure corresponding to this block B naught. Okay. And if B naught is non-pendant, then we can take Y U naught to be positive. Otherwise, we can choose U naught to be a positive vertex contained in B naught. Okay. Otherwise, we can choose another U naught to be a positive vertex contained in B naught. Okay. This is case B, and this case occurs when G is a type 2 graph. The minimizing graph is a type 2 graph. Now, that edge E plus in the block structure, if we remove it from the block structure, because it is a tree, so we get two components. One component contains Phi naught, the other component contains U naught, and the component containing Phi naught will be denoted by T V naught, and the component containing U naught will be denoted by T U naught. And the subgraph of Z corresponding to this T V naught is simply denoted by say H P naught and H U naught respectively. And the path in the block structure is said to be a non-pendant path if all the vertices of the path are points of articulation of G. Now this lemma gives us a crucial information about the Fiedler vector along non-pendant paths in the block structure. Suppose that Z is a restricted graph which minimizes the algebraic connectivity in this class, and if say Y is a Fiedler vector of Z, then the valuations of Y along every non-pendant path in the block structure which starts at U naught in T U naught and starting at V naught in T V naught increases and decreases respectively. Okay. The valuations of Y along every non-pendant path of TBG, the block structure, starting at U naught in T U naught increases, and starting at V naught in T V naught decreases. So this gives us a crucial information about the Fiedler vector along a non-pendant path in the block structure. And then what is a maximal pendant path? Suppose Z is a connected graph made with the given blocks P1, B2, Bk. A path P which starts at V naught, ends at PL in the block structure is said to be maximal pendant path at V naught if degree of V naught is greater than or equal to 3 and degree of V1 up to degree of VL minus 1 is equal to 2 and degree of VL is 1. And this V naught is said to be starting vertex of the maximal pendant path P. This is an example. Suppose this is a block structure of some graph, then this path P which starts at U is a maximal pendant path. because this U has only degree 3 and all other vertices up to UL has degree 2 and this vertex has degree 1. Similarly Q, similarly R, similarly S. Now this lemma says that the starting vertex of maximal pendant paths in the component TU0 is unique and the starting vertex of maximal pendant paths of TV0 also unique. So what does this theorem say? If G is a restricted graph that minimizes the algebraic connectivity in this class, then the maximal pendant paths of the block structure which are contained in TU0 have the same starting vertex in TU0. Similarly, the maximal pendant paths of the block structure contained in TV0 also starts at the same vertex. And then that means this cannot be the situation. Here you see this is a maximal pendant path, this is a maximal pendant path, and they are starting at two different vertices in TU0. So this cannot be a block structure of a minimizing graph. And not only that, this lemma says that the length of each maximal pendant path in TV0 as well as in TU0 is exactly equal to 1. So because of this lemma, these two lemma, we will see that this is the structure block structure of the graph minimizing the algebraic connectivity among all graphs constructed with the blocks B1, B2, Bk with R pendant blocks. Now this graph, which is a tree, is denoted by say PKST, which is obtained from this path P starting at x0 ending at xk minus s minus t on this many vertices, adding s pendant vertices to x0 and t pendant vertices to this ending vertex. And this is denoted as PKST. And this theorem says that among all connected graphs in this class, the algebraic connectivity is minimized for a graph whose block structure is simply PKST for some S and T, and S plus T should be equal to R. This is because of these two theorems only, these two lemmas only. These two lemmas says that maximal pendant paths in TU0 starts at unique vertex. Also, the maximal pendant paths starting at TV0 starts at unique vertex. And not only that, maximal pendant paths must have length exactly equal to 1, and that's why this is the structure we get. So this is our main result. So we got the structure of the graph minimizing the algebraic connectivity over all graphs in this class. And with the help of this structure, we can apply those structure and we get some results which were already proved, and some applications are going to be discussed now. Now, suppose alpha KST means the minimum of the algebraic connectivity of graphs in this whose block structure is this. Okay, suppose this value denotes the minimum of the algebraic connectivity of the graphs in this whose block structure is this. Then this is a strictly increasing function with respect to S and T. And as an application of that, we can obtain that among all connected graphs made with some given blocks, the algebraic connectivity is minimized for a graph whose block structure is a path. And this is what proved by Bapot, Lal, and Poti. in their paper in 2012. And another application, and this application, so this gives us an alternative way to view this well-known fact. Among all trees, the path has the minimum algebraic connectivity because of this theorem proved by Buffett, Lal, and Poti. And this can be obtained as an application of our structure. And another application gives us the Gauss result, and Gauss result which was conjectured by Fallaght and Kirkland in this paper. What it says, among all connected graphs on n vertices with fixed guard G, the algebraic connectivity is uniquely minimized by the unicyclic graph obtained by attaching a cycle of length G to one of the pendant vertex of a path of length n minus Z. See, among all the connected graphs on n vertices with fixed guard G, we can see that minimizing graph will occur at some unicyclic graph, because by deleting edges we can get a unicyclic graph of guards G on n vertices. So a minimizing graph will be a unicyclic graph, and one can see that the unicyclic graphs on n vertices and guards G can be viewed as graphs obtained by using a block which is a Z cycle, and other n minus Z blocks which are edges, and applying our discussions we can get that the minimizing graph has block structure path, and with the help of that we can see that the algebraic connectivity is minimized by a graph, unicyclic graph obtained by attaching a cycle of length Z to one of the pendant vertex of a path of length n minus Z. So with this, I would stop here. These are my references. Thanks.
So, thank you, Dr. Debajit, for giving a talk on algebraic connectivity of graph constructed with given blocks. So, participants, you have any questions for Dr. Debajit? 5 minutes we have. Yeah, I think there's no questions. So I once again thank Dr. Debajit for the presentation. Yeah, thank you.
Okay, thank you very much. Thanks.
Yes, sir. Thank you, Professor Debajit Kalita and Professor A. Gangaran. I also would like to thank Professor Vasudev Budetto for chairing this session. Now we'll have a lunch break. Afternoon session will start at 2:15 IST, and there will be a parallel session. Contributory speakers of session A are requested to join the link named as TES Raghavan Subhall, and participants who are presenting in session B are requested to join Professor R.B. Bapat Subhall. Thank you. Participants, please know, after 4:30 IST, we will be having a common session. So after 4:30, you are requested to join the link with the name CR Rao Hall. Thank you.
I cannot hear anything. What is this?
Dear SK, do you hear
Hi.
me? Oh, hi.
Yeah.
Yeah, I think we are waiting because I think it must be lunchtime or dinner time. I don't know exactly. Probably dinner time. And so I guess that the conference will start in a few minutes or something like 10 minutes.
Yeah. Okay, good. I can hear you. You can hear me, right?
Yes, I can hear you. I can see you, and the presenter, the manager will be presenting the recorded talk, and then we can say a few words at the beginning, and then if there are questions, we can answer at the end. This is the plan.
Nice. Okay, yeah. Okay. You already understand the plan then. Good.
Well, I wrote to, I should have, I wrote to Prashant, and he told me that, this will go like this.
I see.
So good. At the beginning, we can say hello.
Prashant, I can see
yeah. Okay. Yeah. Just I will go mute now, so not to. I'll just stop my mic. There is no need for the moment.
I don't know how to do that. I will not do it anything because. Okay.
Yeah.
No, I'm safe. If I do anything, I may be in trouble.
That's true. You never know exactly.
Yeah. I got up at 4 o'clock.
Wow, my goodness.
Yeah.
4 o'clock.
Yeah, I took my shower and everything, prayers, and then I'm having a cup of tea now. So I did everything. I need 1.5 hours in the morning at least.
Yeah, I'm not actually. I am trying to connect my tablet so that if needed I can write, but I don't know. In fact, I don't know how they can share the screen and so on. So.
Did you hear any talk?
Yeah. Yes, I remember it. Yeah. But I'm just trying to do this, but I can.
Hello, Prashad.
Hi.
Hi.
So,
Hi.
it is early morning for you?
Yeah, 5:45.
Yeah, we had our, in the tea break, we had a coffee.
Good. I'm having coffee also.
Okay. Professor Larai, how are you?
I am fine. I am fine. I hope my mic is open. Yes, I think so. You hear me? Yeah.
I can hear.
Yeah, I can.
Okay, okay. So, and how is going the meeting? It seems that all
Yeah,
is
nice.
fine.
Except for some technical issues, everything is going fine.
Yeah.
You have worked very, very, very hard. Congratulations on this all going on. Best wishes.
Thanks.
Yeah. Maybe I can connect.
Anybody in person also there? In person or everybody on Zoom or everybody on Teams?
Many of the speakers on Teams.
On Teams.
Our local audience and in fact, Susmita Datta was there. I don't know whether you know her or not. You may not be knowing. She is a statistician.
I see.
She was here from Florida.
I see. I see. So mostly it's on Zoom then, mostly on Teams.
Yeah.
Okay. Well, this is all right so long as you are doing such a wonderful job and everybody is coming and participating.
Yeah.
I saw Avi Burman is there giving a talk.
He was there, yes.
And you give me
I
his.
don't know whether he is still there or not. We'll ask him to come in case you want to talk to him.
Yes, Avi Burman is my great good friend. I didn't know that. Okay, so.
Raksha, can you get in Burman? Avi Burman? ಅಲ್ಲಿ ರಕ್ಷಾ ಇಲ್ಲ ಇರಬೇಕು ಬಹುಶಃ.
Send me his email to me whenever you get chance.
Can you hear me, sir?
Yeah.
No, sir. Right now it is not here. I'll bring him in if he joins, sir.
There is echo. Take care of that. Raksha. There is lots of echo as usual. Yeah, now it's all right, I think. Isn't it?
Yeah, I think it's okay. I think I was.
Or she might have gone mute completely.
It's still 4 minutes.
Yeah.
You can relax.
Right.
Yeah.
Anyway, it is also time for talking to each other.
Yes, yes, yes. We need each other. Yeah. Well, I want to thank you for other job you have been doing for me. That typing, we have some papers being typed. Thank you very much.
Yeah, he is. Our Roma Shankar is doing good job. He learned that Devanagari Lipi and he typed it.
I see. Very nice job he has done. We have sent him one paper just yesterday.
Mm-hmm. Who is the other speaker? Sean Fallard. Is he there around?
Three minutes left. Andre, 3 minutes down.
Okay, I'm ready.
Doing the countdown.
Yes. In fact,
Andre, is
no,
it lunchtime for you?
exactly, yes, it's lunchtime, but no problem. Lunch, anyway.
I have some almonds.
Oh, thank you.
You can share it with him.
Yeah, yes, you can share. You can digitalize them.
Digital almonds. So who is publishing it? Prashad, who is publishing it?
You are asking me special issue?
Yeah.
Special issue is from AKC journal. Is published here in Taylor and Francis.
And what is the name of journal is? What is the name of the journal?
Let me recall the complete name.
That's fine.
International Journal of Graph Theory and Combinatorics.
I never heard. I see. Okay, maybe I see. Okay.
That is, but it has got good reputation. Not a very old journal. See, when ELA withdrew for some or other excuses, then I didn't have much time. Just I rushed in, and this is a good journal.
Good.
So, opted for it. And they kindly agreed the moment I made a query. And it's all done.
Okay, okay, good, good. Congratulations also. Bapat is participating?
I don't know whether he is there now or not. He was there since the morning till afternoon.
I see.
Now I'm not sure.
Yeah, I'm here.
Yeah, I can pull him in.
My video is off.
Bapat is there, right?
Yeah, hello.
I can hear his sound now.
Yeah.
Yeah, Raksha, can you bring him in?
How are you, Professor?
For a minute.
I am. Hello, Bapat.
Yeah, hello.
How is everybody?
It's okay. Everything fine. You're fine.
Good.
So where are you now?
I can't. I'm same place where I was.
Okay.
In Dayton, Ohio.
Yeah, right.
You are in Delhi, right?
I'm in Delhi.
Yeah. Okay, 6 o'clock. 6 o'clock. I mean, my time is 6 o'clock. Your time is whatever your time. My time is 6 o'clock. Get ready. Mine is 6 a.m. Yeah. Okay. Well, you can announce whatever you want to. You want to announce something?
Yeah, I'm looking for checks also. Where is the chairperson? Krishnan, are you here around? Shivaram Krishnan.
He's not joined yet, sir.
Then in such case, we can request Bapat to chair, in case he doesn't turn up in 1 or 2 minutes.
Yeah, I will introduce and then may I have to go toward the end. So, but I can start,
Yeah.
So first, Raksha will say something.
So welcome back to the last session of today. So in this session, we have invited talk from Professor S.K. Jain from Ohio University, USA, and Professor Andrew Leroy from University of Artois, France. Professor S.K. Jain is a distinguished professor who has served at Ohio University, Department of, one second, sorry sir, there is some echo, I'll just. So Professor S.K. Jain has served in University of Ohio University. He also served as Director of Center of Ring Theory and its Applications. Dr. Jain has authored more than 135 research articles that have been published in professional journals. He was awarded the Outstanding Graduate Faculty Award at Ohio University. He is an executive editor of the Journal of Algebra and its Applications, World Scientific Press, and that of Bulletin of Mathematical Sciences, Springer Verlag. He is also serving on the editorial board of Electronic Journal of Algebra. He is a life member of the Indian Mathematical Society. He is also a member of American Mathematical Society. And Professor Andrew Leroy is from University of Artois, France. His area of interest is the theory of rings. He has more than 50 publications related to the topics rings. He is an expert in the fields of matrix theory, abstract algebra, information theory, etc. Today they will be delivering a talk on matrices generated by conjugates. Another speaker of this session is Professor Sean M. Follett from University of Regina, Canada. He has written a book titled Totally Non-Negative Matrices, which was published by Princeton University Press. His area of interest are matrix theory, discrete mathematics, graph theory, combinatorial matrix analysis, etc. Today he will be delivering the talk on the minimum number of distinct eigenvalues of a graph. I now request Professor R.B. Bapat to chair this session. Over to you, sir.
Thank you very much. Pleased to chair this session. Happy to see Sir Jain after maybe 3 years. I don't remember. But very good to see you, sir, and Professor Andrew Leroy. So I'm pleased to chair this afternoon session, and we will have the first talk on matrices generated by conjugates. Over to you. Thank you.
Hello, everyone. So first of all, let me thank you very much for the opportunity of speaking here today. So the thing I will say today are results from joint work with my friend S.K. Jain from Ohio and Abdulaziz University.
The sound is not clear.
As matrices generated by conjugates of any matrix. So, in fact, our aim is to give an elementary proof of the following theorem.
Sir, we will sort it out. One second.
Hello, everyone. So first of all, let me thank you very much for the opportunity of speaking here today. So the thing I will say today are results from joint work with my friend S.K. Jain from Ohio and Abdulaziz University. So, in fact, today the title is Matrices Generated by Conjugates of any matrix. So, in fact, our aim is to give an elementary proof of the following theorem. So, if you have an algebraically closed field and A as a matrix which is singular and B another matrix which is of smaller rank or equal rank, then B is a product of conjugates of A. In fact, this result is valid more generally for matrices with coefficients in division rings. A proof of this more general theorem was given by Araujo and Silva in Communications in Algebra in 2000. So here our aim is just to give an elementary proof of this result. So the first thing that we have, you have two matrices A and B, and you want to show that B is a product of conjugates of A. So we will first prove that B is a product of idempotent matrices, such that these idempotent matrices have the same rank. So, okay. For this, since A is singular, of course, B, which is of smaller rank, is also singular. And then by suitable conjugates of B, you will have that you can just choose B to be a matrix of the following form: B is D, C, 0, 0. This is just because B is singular. And now you go by induction. So we want to show that B is a product of idempotent matrices of same rank as B. So if n is 1, so you just have B as an element from F, and since it's singular, well, you have no choice, B must be 0. And in this case, there is nothing to say, to show. Now, if n is bigger than 1, then you go by in two cases. The first case, if D is singular, then by the induction hypothesis, you can write D as a product of idempotent matrices, such that the rank of this idempotent matrix is equal to the rank of D. And in this case, you just write your matrix B, which is D, C, 0, 0, as E1, C, 0, 0, E2, 0, 0, 1, and ER 0, 0, 1. And again, in this case, you distinct two cases again. The first one is if the rank of D is smaller than the rank of B, then you have no choice, because here your C is in fact a column. So C is a column vector. You see, you just have the bottom row 0, and this C here is in fact a column. And so if when you are in this case and the rank of D is smaller than the rank of B, then the rank of B is just the rank of D plus 1. You cannot increase the rank of D by more than 1, just adding a column. So, and in this case, you easily realize that all these elements, these matrices on the right-hand side are idempotent matrices, and they are of the right rank. This means the rank of B. Now, if the rank of D is equal to the rank of B, then this means that this matrix B here, which is DC00, and the matrix B is the same rank as the rank of D. This will mean that C, this column C, must be a multiple of D. So C must be equal to D times Q. And in this case, you can just decompose your matrix B in this form, and everything is again fine. You have idempotent matrices here, and they are of the right rank. Now, the second case is the case when D is not singular, but is invertible. And then in this case, well, D is invertible. You just write your matrix B as decomposed like this, 0, D, 0, 0. And then this matrix here in the middle, 0, 0, IN minus 1, 0. And here, IN minus 1, D minus C, 0, 0. So the first matrix here is in fact a matrix that can be treated as in the previous case, when the left corner you had a singular matrix, and everything is fine for that matrix. It can be written as a product of idempotent matrices of the same rank as the rank of B. And this matrix here will be is in fact an idempotent matrix, again of the right rank. And as long as the middle matrix here is concerned, you just can conjugate it so that you again arrive to a matrix which can be treated as in the previous case. So when you will conjugate B by this P here, you will have that the conjugate of B is a product of idempotent matrices, which are all of the same rank of B, and so the same is true for B, of course. So this proves the claim. So our matrix B can be presented as product of idempotent matrices, which are all of the same rank as B. Okay. Let me remark before going on to the second part that the proof above works for F being just a division ring. So we don't use that F as algebraically closed, and even we don't use throughout this first case that F is commutative. So you can take even a division ring. The proof will work. Okay. So now in the second part, of course, we will use our hypothesis. And let me first remark that, and first recall maybe that what we want to show is that the matrix B, which is a smaller rank than the rank of B, than the rank of A, can be written as decomposition of B. I'm just looking where it was written, that all these idempotent metrics here are products of conjugates of A. Okay, and the first thing I want to show or to convince you is that in fact it's enough to work with the case when the matrix EI which appear there are in fact of the same rank as A. In other words, we have to show that all these idempotent matrices E1, ER are product of conjugates of A. And what I want to tell you is that it's enough to show that if you can do this for an idempotent matrix of the same rank as A, then you can do it for any idempotent matrix of smaller rank than the rank of A. So, okay, well, this is very easy because, in fact, if you have two idempotent matrices E and E prime of size n, such that the rank of E prime is smaller than the rank of E, then in fact E prime will be a conjugate of a product of conjugates of E. And this is easy, and I will leave you this as an exercise. It's easy because the first thing is that E is equivalent to this kind of matrices here, and E prime is equivalent to this kind of matrix. And then with playing a bit with the product of the matrix E and conjugate of this matrix, then you will get E prime. You will just make appear some zeros on the diagonal. Okay. So now what we have to show finally is that the matrix IR000 is a product of conjugates of A, where R is just the rank of A. Now, since A is singular, 0 is an eigenvalue of A, and the Jordan canonical form of A, you can write it like this. So you first collect all the Jordan blocks which are concerned with a non-zero eigenvalue, and this gives you the matrix A1, E1, and you put together all the Jordan blocks of A which are concerned with the singular value 0, and you call this A0. So the A0 is just of this form, so you have all the Jordan blocks, and they are concerned with the 0 eigenvalue here. Now, with this matrix, this GI, if you write the GI and you multiply it by a conjugate of GI, you will get a matrix which has 1 on the diagonal and just 1 0 at the end of the diagonal. So it's a diagonal matrix with 1 everywhere except on the last row. And what is the PI? The PI is just the matrix which has ones on the entire diagonal. Now, so you just can check that. And the rank, well, the rank of this conjugate here is just the same as the rank of GI. So you can do this for every GI which appears in the Jordan block associated to 0. And if you take Q, which is this invertible matrix, then you will have that A0, QA0, Q inverse as a diagonal matrix with only 1 and 0 on the diagonal. You see, you will just collect all this 1, 1, 0, 0. This matrix here, matrices here, you will be collecting all along the diagonal. And necessary, and you can arrange so that finally you get a matrix of this form here, with only the ones and then the zeros at the end. And the number of ones is, of course, the rank, and so this rank is preserved, and the number of ones you have this is just the rank of A0. Okay. Now, so this treats the case of the A0 part of the Jordan decomposition, this part here. And for the moment, you don't move, you don't touch at A1. So when you take the product of conjugates of A, you use the matrix PI and the Q here that you got, and you complete them with this Q, you complete them with the identity on the level of A1, right? Doing this, you will arrive at your matrix as in the product of conjugates of your matrix will be of this form here, and the A prime, if you look a bit at the rank, it will be of the same rank as A. And of course, since F is commutative and algebraically closed, you can assume that A prime is upper triangular with non-zero elements alpha 1, alpha r on the diagonal. And I recall you that R is the rank of A. So, okay, you have just this matrix A prime, which is upper triangular with non-zero element alpha 1, alpha r on the diagonal. And then you will try to change a bit this matrix by taking products of conjugates of it. And in order to get, I remember you that what we want to have is to obtain the matrix IR000, where R is the rank. Okay, so what you do is you introduce, for any, in fact, matrix, rectangular matrix of size R and n minus R, and W of size n minus R, you introduce the invertible matrices IR, V0 by n minus R, we call it TV, and you introduce TW, which is IR, 0, W, I, n minus R. And you take the product of these conjugates, and doing this, you can check that what you get is this. So it's a matrix which is of the same form as the one we have already. I mean, A prime 0, 0, 0. But here, instead of A prime, you have this. And so carefully choosing, in fact, V and W, we will, and making product, we will see that it's possible to have, in fact, the identity in this place. Okay, so let's do this. So first, for every I from 1 up to R, so for, I recall you that this matrix here, which is here, is of size R, and it's of rank R. And for every, I mean, A prime was of rank R, sorry. And then for any lambda I, you choose this matrix. You construct this matrix, which is an R times n minus R matrix. And you construct this matrix here, Wi, which is just a unique matrix which has 1 on the first row and em column. And here the Vi was a matrix which is a lambda I on the eth row and the first column. And then when you take the product and you make the small computation that you have here with this Vi Wi, you will have that you get a matrix which is upper triangular, and with on the diagonal the square of all the alpha I except, or alpha j, and except on the position I where you have 1 minus lambda I alpha I squared. Okay, you can do this for any I from 1 to R, and if you take the product now of this matrix, what you have is an upper triangular matrix with this element here on the diagonal. Now, and remember that the lambda I are just any elements in F. So let me go back to show you what we want to show. We have a matrix by taking some conjugates and products of conjugates of the matrix, the initial matrix A. We arrive to a matrix of this form, A prime 0, 0, 0, and where A prime is in fact an R by R an R by R matrix with which is upper triangular with non-zero element on the diagonal. And now you take this product and here, and you have that the product of all this A prime R is of this form, right? And remember you also that this matrix here, which is here, is also a product of conjugates of A, right? Okay. So and now if you take any element in F, you can choose now the lambda I in this way. And then when you make the computation, you will have just that your matrix is second that you will get using this lambda I will be in fact a matrix which has all on the diagonal, or will have only the BI, the beta I, which are chosen. And so if you choose them to be distinct, then you have that this A second will have all its diagonal elements which are different, distinct. And so this matrix A second will be diagonalizable. And hence there exists a P such that P A second P inverse is just this diagonal. Similarly, you can find a Q such that Q A second Q inverse is this matrix. And hence, finally, when you take P A second P inverse Q A second Q inverse, you have just IR. And then, of course, retracing our steps. So by this, I mean that we have seen that the conjugate of product of conjugates of A was this matrix here. And now we have seen that product of conjugate of this matrix is in fact a matrix IR. You see, you have here this, you get IR. And so in fact, it's easy to get from there that the conjugates of a product of conjugates of A prime 0, 0, 0 is in fact equal to diagonal of IR and 0. So this is exactly what we wanted to do. And so you see that we have proved our theorem. Thank you for your attention, and I wish you a good meeting. Bye.
Are there any questions or comments from the audience? Any comments or questions from the audience?
Raksha?
Participants, are there any questions? Please raise your hands. Participants.
I have one. Are these matrices over arbitrary ring, or are they real or complex matrices? In your case?
So maybe I can answer. So at the moment, so far, for having the B written as a product of conjugates of A, it is known when in fact you have a division ring. So you take matrices over a division ring.
Okay.
But for
involution is required. If I'm correct, involution is required. Involution.
Which an involution?
With the involution. So yes, I think that the result is quite general for any matrix ring over a division ring. But if you just want to have the product of idempotents of the same rank, then there are other rings for which I know that this is true, that a singular matrix can be presented as product of idempotents matrices. This is of the same rank. This is true for not only division rings, but for other rings.
Do you expect this non-zero definite property for that involution? Non-zero definite property means summation ai bar that is equal to 0 implies all a's are 0.
Oh, I see. So you want to? Oh, I see. So you take conjugates. I don't. This I don't know. I'm not sure. This gives me a feeling that you have something with the positive thing and some kind of this relation, and I have some doubt about going this direction. But because I know that some of the things which are related to positivity are wrong, so I'm not sure.
No, I'm not assuming positivity. Only non-zero definiteness.
I see. So you are asking if you assume that the matrices which are involved are just positive definite, right? I don't know. I don't know. I cannot. I don't.
No, it is non-zero definiteness. That is what you see. Only when such assumption is made, we can talk something. Generalization can be done, like in the case of Moore-Penrose inverse.
Oh, yeah.
Otherwise, Moore-Penrose inverse doesn't exist for such matrices.
I see what you mean. But I have no idea.
Okay.
Maybe
Anyway,
Stephen has
I'll
some
go
idea.
through your talk once more critically, and I'll get back to you.
Okay, sure. Thank you.
Yeah.
You're welcome. Thank you. Maybe SKJ has some comments on the
he is trying
on
to
this
say
topic.
something.
Oh.
No, you are muted, Professor Jain.
He doesn't.
You'll have to unmute yourself.
Yeah.
Is it okay now? Can you hear me?
You can hear.
Okay. Okay. Sorry, I was speaking before also. I did not know I'm muted. Anyway,
Yeah, I observed.
What I would say that this theorem which we have gotten is can be put inside any undergraduate book. When you look at the proof over the field, it can be taught in a 1 hour class easily. That you can put as a matrix a conjugates of a fixed matrix. Okay, this is what our old question we were working on before. We left it, but then somebody proved it over semigroups. But he's using the semigroup theory. However, this proof what we have is just purely matrix theory. Of course, we need complex field for that because we need Jordan form. Because of Jordan form, we need the complex field. Regarding idempotents, we can use many rings which are not fields. They are true that every element product of idempotents matrix. However, for the getting this result that every matrix is a product of conjugates of a fixed matrix, you need complex field by this proof. But other proof of semigroup theory doesn't need that.
Yeah, good. Thank you.
Okay, so
Any other is raising their hand? I don't think so.
Yes, sir. I think there are no questions from the audience, sir.
If there are no further questions, we will thank Professor Jain and Professor Leroy again for this being present and delivering this. We will move on to the next topic. Thank you.
Thank you for listening.
Thank you. Thank you for having me. Sure.
The next talk is by Follett.
Right.
Yeah.
Rakshak, can you bring him in? Yeah. Professor Sean is here, but he is muted. He had to unmute himself. Yeah.
Morning.
Raksha has already given your introduction in your absence.
Very early in the morning. Yeah.
Good morning. Is it very early morning for you?
Yeah, 5 a.m. Yeah.
5 a.m. Yes. No, 5:30. You mean?
5:30. Yeah.
You know.
Okay.
How
With
is
their
everyone?
permission, we can go ahead with his talk.
Yes, please.
Okay, we go ahead.
Yeah. Right.
Okay, so
Welcome to my talk on the minimum number of distinct eigenvalues of a graph. It's my pleasure to join everyone at this conference in Manipal, India. As I had hoped, I wish I could have visited India at this time, but sadly, because of the pandemic, I'm not able to. But hopefully one day I will get down and visit you folks in Manipal and elsewhere in India. I'm talking about the minimum number of distinct eigenvalues of a graph, and there's plenty of topics and current ongoing research in this topic. I will highlight a few topics regarding this parameter, as you see on the table of contents slide. It's not a comprehensive list, but it'll give you a sort of a broad overview of some of the current research and some existing research on this topic. Let's begin with some of the background. The idea here is you have a graph that's fixed and you associate a collection of matrices to that graph. And the parameter that I'm interested in is for each such matrix, you calculate the number of distinct eigenvalues. And then through all of those matrices, you choose the one with the smallest number of distinct eigenvalues. And for us in this talk, the matrices we're going to associate to the graph are n by n real symmetric matrices. And their connection to the graph is as follows. For the off-diagonal entries, the ijth entry is non-zero if and only if there's an edge from vertex I to vertex j. And naturally, that off-diagonal entry will be zero when there is no edge. I am not concerned about the main diagonal. They are free. You can choose them to be non-zero or zero as you see fit. And I'm not concerned with the labeling of the graph, as relabeling of the graph does not change the parameter that I'm interested in. Now, for this class S of G, there are other parameters of interest, also of current research interest, and they are capital M and little mr. Capital M, as indicated here, is the so-called maximum nullity of a graph, and it's simply the largest possible nullity over all matrices in the class S of G. By the same token, instead of calculating the nullity, you can calculate the rank, and one of the parameters of interest is the smallest possible rank, and we refer to that as the minimum rank. Now, the basic equation you learn in linear algebra is that the rank plus the nullity is the number of columns, and of course, that still applies to these two parameters as well. So if you're studying capital M, you're also studying little mr at the same time. There's a lot of research has been accomplished on capital M and hence little mr, and I've indicated just a couple of works here. Capital M has been characterized, or the graphs for which capital M is the number of vertices minus 1 or the number of vertices minus 2 or 1 or 2, they have been fully characterized. There's lots of research on other values of capital M, but there's been no formal resolution for other values of capital M. And long ago, capital M equal to 1 was resolved by Professor Fiedler in 1969, where he showed that the only graph where the maximum nullity is 1 is precisely the path, the simple tree on n vertices. But for us, we are looking at the minimum number of distinct eigenvalues, and so I'll define that here. So for a square matrix A, and of course we'll consider only symmetric matrices, QA just denotes the number of distinct eigenvalues of that matrix. So you just calculate the eigenvalues and determine the number of distinct eigenvalues, and you call that little q. Now, for us, when the graph is fixed, you calculate QA for all matrices in S of G, and then you take the smallest such QA, and that's called the minimum number of distinct eigenvalues of a graph. And it is clear, just by simple counting, that the number of distinct eigenvalues of a graph has to be between 1 and the number of vertices in that graph. And the only graph for which there is just a matrix realizing it with one eigenvalue is, of course, the empty graph, because your matrix would have to be scalar. And in particular, we can appeal to Fiedler's previous result and show that the only graph for which the minimum number of distinct eigenvalues is n happens to coincide with the graph with the maximum nullity is 1. So in some regard, if you're studying little q, you're also studying relations to those other parameters. Now, the minimum number of distinct eigenvalues of a graph has appeared elsewhere in the world of combinatorial matrix theory in connections with the diameter. So here I define the diameter of a graph, and it's a well understood concept. It's basically the sort of largest distance in the graph, if you will. And for the adjacency matrix, the very classical adjacency matrix, it's known that the number of distinct eigenvalues of the adjacency matrix is at least the diameter of the graph plus 1. And the proof is very simple, straightforward, and it sort of makes use of the notion of the minimal polynomial of a matrix. And it really has not a whole lot to do with the adjacency matrix because it applies to any non-negative matrix. So this was a springboard beginning point for lots of folks doing research on this topic, because you might ask yourself, look, does this idea, relationship between Q and diameter extend beyond just non-negative matrices associated with a graph? And the answer is it sort of does, but not exactly. And you can, if you insert an additional hypothesis that diameter is the path that realizes the diameter is somehow unique, then you do get this same relation that I referred to before. But of course, it doesn't have to happen in general. And here's some additional results. For trees, you get that same inequality that existed classically. However, for trees, there can be a gap, it can be a large gap. And it turns out that in general, there is no relation formally between the diameter and Q, because for the hypercube, as indicated at the bottom, the hypercube has diameter n, but has little q equal to 2. So in general, there's no relation. Now, referring back to trees, it's been known for a long time that the maximum nullity of a tree is the same as the path cover number, which turns out to be the same as this also interesting parameter called zero forcing, which is not going to rise throughout the talk. I simply note that. And for a long time, trees with diameter at most 5, it was known that this equality held, that actually Q was equal to the diameter. And a long-standing open question was, boy, does that equality hold for all such trees? And myself and a postdoc back in 2004 proved that it need not be true, that there is a tree, here it is here, where the diameter is 6, but little q is 8. So it's no longer the diameter plus 1, but now it's the diameter plus 2. After our paper appeared in 2004, some additional work showed that if you sort of keep extending this tree, which is referred to as a binary tree, you keep extending it for longer and longer arms and so forth, you can actually get this gap to grow as much as you want, based on the number of vertices. And so as research moved beyond trees, we asked a number of questions. And one of the questions we asked was, okay, so let's look at graphs with small values of Q. And that turned out to be a very interesting class to study. So I already told you that if Q is 1, then you're only talking about the empty graph. So the next possible value of Q to study is Q equal to 2. And if you have only 2 eigenvalues, then you have only 2 multiplicities. And we talk about this bipartition of n consisting of 2 multiplicities. And so if you fix Q equal to 2, then you can realize a matrix that has precisely two eigenvalues, and we can assume those are the multiplicities. And then you can look at this, one of these multiplicities, whichever one is smaller, we call that the minimum multiplicity bipartition. And if you can start, once you fix Q equal to 2, you can start going through the various values of MB. MB equal to 1 and 2 are characterized and by previous works, and my current postdoc and I are getting close to, I hope, resolving MB equal to 3, but it is not straightforward. The complete multipartite graph, where each part has size k, is a very special and highly structured graph that has Q equal to 2 and multiplicity bipartition number equal to k. So the multiplicity bipartition can grow the number of vertices. And I'll just mention quickly that the fact that the hypercube has Q equal to 2, as I noted previously, with multiplicity bipartition, it happens to be n over 2 and n over 2, where it happens to be half the number of vertices, half the number of vertices. This is related. This idea is related to a so-called sensitivity conjecture, which was recently resolved by someone else. Now, going back to graphs with 2 distinct eigenvalues, this is an extremely interesting class, and I shall say it is unresolved currently. So we do not have a characterization on the graphs for which Q equals 2. Here's a few sort of comments and properties associated with such graphs. If your graph has Q equal to 2, then the minimum polynomial has degree 2. And so you can rewrite this in terms of the fact that a squared must be in the span of a and I, which is what I've written here. But in another way to think about it is that the graph of a squared, however that should be, has to sort of be the same as the graph of a, is another way to think about it. So that's a property of the graph with Q equal to 2. Item number 2 is extremely interesting because it sort of connects the notion of Q equal to 2 to a really important matrix topic. So if Q equals 2, then the class S of G admits a real orthogonal matrix. And because S of G is symmetric, that orthogonal matrix will also be symmetric. And that is extremely interesting, but still it doesn't help to sort of resolve the characterization. Here's another property associated with graphs that have Q equal to 2. And it's basically just a straightforward neighborhood condition. But I should say that it really boils down to the fact that, if your matrix is orthogonal, then you'll have certain orthogonal columns or rows, and if you take into account the pattern, a little inequality like this will pop out. It's not that significant. I just want to put up one slide of some very current research going on. So there's a group of us working as part of an American Institute of Mathematics research community, and we're working on the so-called Q equal to 2 allows problem or requires problem. We're working on both. And the Q equal to 2 allow problem asks the following question. Fix a graph on n vertices. So you fix the number of vertices, and you ask how many edges are necessary to allow Q to be 2. By that I mean, what are the fewest number of edges you need in order to make sure that there is at least one real orthogonal matrix in the class S of G. And we have the following theorem that bounds from below the number of edges in terms of the number of vertices. You can see it here on the slide. And we have characterized the graphs that meet the lower bounds. So those bounds are tight. You can't do any better. And this is just giving you some insight into sort of more additional properties associated with graphs that have Q equal to 2. Now, when we were studying the Q equal to 2 problem, it became clear that as the graph had more edges, like for example, the complete graph has Q equal to 2, then you were more likely, and certainly the allows problem in the previous slide indicated that, if the graph has lots of edges or is so-called dense, then it's more likely for the class to admit an orthogonal matrix. And so one operation of a graph that we started considered was the join of two graphs, and I highlight that here. So the join of two graphs is you just take two copies of the graphs G and H, and you would provide every edge between those two graphs. And a theorem that was developed in part by a group here, this discrete math research group, and then by some colleagues later that worked out a much cleaner idea. We showed that if you have two connected graphs G and H on the same with the same number of vertices, then the Q of their join is 2. So no matter what the Q of the original graphs were, as soon as you take their join, the value of Q drops down to the smallest possible value, Q equal to 2. So this led to a lot of interesting research, and so people began to ask, well, how necessary is it that G, the size of G and the size of H are the same? And it turns out it's fairly important. It's not absolutely critical. You can work out a little bit fewer conditions, but for example, if you take the join of two paths, one on one vertex and one on n vertices, Q is roughly n over 2, so certainly not 2. And there's lots of current research going on the join of two graphs, in particular, just the join of a graph with a vertex. And there's, we're starting to understand a lot more about the behavior of what happens. And it does appear that as you join vertices to a graph, well, of course, eventually you get down to Q equal to 2 when you have the graphs of the same size. But it seems like you get to Q equal to 2 much quicker than that. So we're working on that currently. Of course, once you start sort of dealing with joins of graphs, other kinds of structured graphs appear, and a very important case, or sort of first case, if you will, is threshold graphs. Threshold graphs are defined in the following way. You start with a collection of vertices, and then you sort of take a vertex and you either add it to the graph as an isolated vertex, or you join it to the graph that you have as a dominating vertex. And so that's how you build these threshold graphs. So in a way, you can think of threshold graphs as just being created by a sequence of vertices, or just a binary sequence, as I indicate here, where a vertex has label 0 if it's just an isolated vertex that you add, or it has label 1 if it's a dominating vertex. And for the next slide, the next couple of slides, I'll just associate the creation sequence to the graph as a matter of associating the two. So threshold graphs are highly structured and very sort of straightforward kinds of graphs, where either you have an isolated vertex that you add, or you add a dominating vertex. And with a current postdoc of mine, we were able to work out the Q value for plenty of threshold graphs. We don't have complete characterization, unfortunately, but for the following threshold graph, so-called trace2 threshold graph. So trace just refers to the number of ones. So here there are 2 ones. We showed that, so here you take a bunch of isolated vertices, then you join a vertex, then you take another bunch of isolated vertices, and you join a vertex. We were able to work out explicitly the Q value for these graphs. And the point I want to make here is that Q is small, right, relative to the number of vertices, because Q1 and Q2 can be any size you wish. And that's of interest to us, that even these graphs have small Q. And so, you can work out further. So here's just some bare min cases. But what the point I really want to make, as I highlighted, is that Q stays small for these highly structured graphs. Here's this, in this case, is trace 3. We've been able to work, and it still seems that Q is small. You see here. Now, as I'm going to get to later in my talk, there's these very important sort of generic type properties associated with a matrix called strong spectral property, strong Arnold property, strong multiplicity property, and so on. And whenever you can exhibit a matrix with these strong properties, that's helpful for producing additional matrices that have very, very important and nice properties. So for the graph here, the threshold graph where you alternate isolated dominating, you can work out that actually Q of that graph is 3. So here is a threshold graph where you have lots of ones. The trace is half the number of vertices, but the Q actually also stays small. But much more is true, actually. The matrix that we found that realizes Q equal to 3, which turned out to be the minimum, had what we refer to as the strong spectral property. I'll define that a little bit later. But once you have a target matrix that exhibits this strong spectral property, then you can apply to supergraphs. What I mean by that is you keep the graph fixed, you keep the number of vertices fixed, but now you get to add any edges in any manner you want, and Q does not increase. So this allows for a lot of graphs now to have very small Q. And so this was extremely interesting. And going back to the small Q problem, we realized very early on that if you had lots of ones, if your trace exceeded half the number of vertices, then your Q was 2. And just notice here that this graph is right on the threshold. Okay. So going back to the SSP and SMP paper, properties, we want to tie them back with the little Q parameter. So maybe about 20 years or 25 years ago, Colin Deverdier developed a couple of papers where he looked at a certain kind of nullity parameter that's now known as the Colin-Deverdier number. And he sort of tied this nullity to certain topological properties of a graph. And I can give you an example. So he hit the class of matrices he was interested in are so-called generalized Laplacians. And these generalized Laplacians needed to have an additional property called the strong Arnold property, as I highlighted here. If you had a generalized Laplacian matrix that had the strong Arnold property and you calculated its nullity, then that nullity sort of connected to certain topological properties of a graph. And one of the theorems he presented, which was extremely interesting, he showed that if you take the maximum such nullity over all the classes, and if that maximum is at most 3, then your graph was planar. And moreover, the converse was true. So that was he provided a sort of an algebraic characterization of when the graph is planar. And later on, myself and a group of folks developed sort of analogous strong properties, but instead of tying things to rank or nullity, we really wanted to concentrate on eigenvalues. And so one of the properties we came up with was the so-called strong spectral property. And I'll go through the definition carefully here so we can make sure we understand it. So a matrix satisfies the strong spectral property if the only solution to the series of equations here is x equal to 0. And here x is required to be symmetric. Okay, so the multiplication here is the Schur product. So this is the entrywise product between A and X, the entrywise product between the identity and X, and this is the commutant, AX minus XA. So you set these equations, the Hadamard product of AX is 0, the Hadamard product of IX is 0, the commutant is 0, and if the only solution to that series of equations is X equal to 0, then you say this matrix has a strong spectral property. Now, I understand that just looking at those equations, they might seem like they come out of thin air, but they actually are tied to a very algebraic, very strong algebraic property, where two particular manifolds are required to intersect transversally. And those manifolds are the so-called isospectral manifold, which is the collection of symmetric matrices that have the same eigenvalues, and the pattern manifold. And that's the graphs, the matrices that respect the pattern associated with the graph. In a very similar way, you can describe what we call the strong multiplicity property, which is very similar to the strong spectral property, but you add one more condition. And here, of course, what we're trying to do is control the minimum polynomial. And these properties, the strong spectral property, the strong multiplicity property, and so forth, they are related. They're not the same. They are distinct, but they are related in the following way. So the strong spectral property controls eigenvalues, if you will. The strong multiplicity property controls the multiplicities, and the strong Arnold property controls the rank. And so one of the things we were able to do in our focused research group is we were able to come up with the following theorem, which is analogous to what Colin de Verdier developed when he was interested in this nullity parameter that I mentioned previously. So you fix a graph and you let H be any supergraph. So in this case, supergraph just means it's the same number of vertices, but you're allowed to add edges that weren't there previously. Now, if the matrix A you started with had the strong spectral property, then in the supergraph, there is a realization associated to that supergraph that has the same eigenvalues. So the idea is you fix a graph, you fix a matrix respecting that graph. If this matrix has the strong spectral property, then there is a matrix associated to the larger graph, the one with more edges, that has the same eigenvalues. And that's the power of this strong spectral property. Furthermore, the realization that I referred to above also has the strong spectral property. So then you can repeat this process as you move on. But be aware that I'm not changing the number of vertices in this context. Of course, if I change the number of vertices, I change the number of eigenvalues in general. So I certainly can't hope for the same collection of eigenvalues. However, there are results where if you actually increase the number of vertices, you can find a realization that has the same original set of eigenvalues plus some new ones. We can argue in that regard. In the very same manner, if you have the strong multiplicity property, then you can find a realization that has the same ordered multiplicity list as A. So these strong properties are extremely handy as you sort of move through certain graphs and then extending to supergraphs. So here I just want to present an example because it'll come back later in the talk when I get to large values of Q. So consider the star, the so-called graph K13. So you have a vertex connected to 3 vertices. Its adjacency matrix has these eigenvalues. That's straightforward. It's a 4x4 matrix. And I claim that the adjacency matrix A has what's so-called strong spectral property. So how do I prove that? Well, I have to show that the only symmetric matrix that satisfies these conditions and commutes with A is the 0 matrix. Well, if X satisfies the conditions here, then X has to look like this, just based on the pattern of A. And then if X commutes with A, because A is the adjacency matrix of the star, you can show that means all row sums and column sums of X are 0. But if you look at this matrix and you go through the conditions that all row sums and column sums are 0, you can conclude that X has to actually be 0. So what this verifies is just applying the previous theorem that I mentioned, is that if you add any edge to the star, then there is a realization that has this spectrum. So, for example, the graph I drew below, I've just added a couple of edges to the star, and I now know there exists a matrix that has this realization, and it has the strong spectral properties. So this is a simple application of the theorem I referred to a moment ago. Now, we are, of course, interested in this parameter q. And so what we do in order to get back to little q is we calculate two new parameters, q sub m and q sub s, where these guys respect the so-called strong multiplicity and strong spectral properties associated with the matrix. And clearly, you have that little q is the minimum over all such matrices. So little q bound is a lower bound for both of them. But because the SSP implies the SMP, you get this relation as well. So we are interested in little q. And so one way to sort of find out information about little q is to figure out little qm and little qs. And we've done that for many classes of graphs. And that's the kind of approach you can take. But what you're really interested in is to use the power of the strong properties. And so there's a theorem we proved that you actually can get monotonicity on subgraphs. And here the important thing to bear in mind is I'm changing the number of vertices per se. So here the way that I write the theorem is, suppose G is a graph and H is a subgraph of G. And it can be on fewer vertices. Then you have this relation in between Q, QS, and QM. And of course, there's a penalty to pay depending on how many, the gap between the number of vertices of G and the number of vertices of H, right? So if little m is very small, then this number, grows, is large. So there is a penalty to pay, but we do learn something. And so you can rejigger these inequalities here to show that if H is a subgraph of G, then these relations hold between the parameters QS of G and QS of H. And so what I want you to observe, is that it's not little q that's monotone like the nullity was in the Colin-Deverdier result. It's this difference that's monotone. Okay, so what does that imply? Well, it says the following. Suppose you have a subgraph where this difference is large, let's say. Suppose you notice that there's a subgraph H where this difference is 6, let's say. Well, then that difference up for the original graph has to be at least 6. And so that's where this inequality is of interest. And that is for studying large Q. And so that's where our final topic will lie. So if we go back, when I defined when I defined the parameter Q, I mentioned that there was a theorem from Fiedler in 1969 who showed that the only graph where Q is the number of vertices is the path. And we can reprove that theorem now. And here's the proof. It's 3 lines long as indicated, but it uses some more sophisticated machinery. So we're going to try to prove that if Q is the number of vertices, it has to be a path. Well, suppose the graph contained a vertex of degree 3. If it contains a vertex of degree 3, then it has to contain K13 as a subgraph. And then we can apply the adjacency matrix that I referred to in the example previously and show that there is a matrix that satisfies the strong spectral property that satisfies this inequality, that Q of S is at most G minus 2, right? And therefore, if the graph had maximum degree 2, therefore, if the graph had a vertex of degree 3, there's no way that little q could be the number of vertices. Thus, in the graph we're talking about, the max degree has to be at most 2. But if you have a connected graph with only the maximum degree 2, then this can be only one of 2 graphs, the path or the cycle. And you can show very easily that the q of the cycle is much smaller than n. It's in fact roughly n over 2. And therefore that leaves only the path graph Pn. So that's a proof in some regard, a reproof, if you will, of Fiedler's original theorem. And in fact, we were able to work a little bit harder and show that we were able to characterize the graphs where Q was the number of vertices minus 1, and those are sitting right here. So the way the theorem is written, it's written as an inequality because, of course, we applied that SSP theorem, monotonicity theorem that I mentioned previously. And so you can show that the only graphs with Q having that Q equals G minus 1 are the graphs here B, C, D. Because of course the path has Q equal to the number of vertices. And that takes us to the end of the talk. So I went through very quickly sort of graphs with small q and graphs with large q, and sort of I give you a taste of sort of what's happening, what's happening out there in terms of the research of Q. And as I close, there's of course lots of existing research continuing. The multiplicity partitions that I mentioned, of course, I mentioned when the case of Q equal to 2, but there's also studies going on for Q much larger than 2. And a current question that's really of interest is, can you achieve any partition associated with a graph as long as that partition had at least Q parts, right? And for example, it is known that you can achieve the partition 1, 1, 1, 1 multiplicity by partition where every eigenvalue is simple. But there's still lots of questions to ask in terms of multiplicity by partitions. In this talk, I talked about Q equal to 2 and so forth. But as I said, that the characterization of graphs with Q equal to 2 is still unresolved. And so there's also work ongoing in terms of other values of Q. A current research topic of interest that I've been working on with a group of researchers is gaps in Q. So suppose you have a graph. Suppose it has 10 vertices, and suppose little q is 3. So is it possible to find realizations A so that Q of A is 4, 5, 6, 7, all the way up to 10? And that's still unclear whether that's true or not. And so we're working on whether there might exist possible gaps in this Q. There's a new parameter that I'll mention quickly in passing called capital Q, which is actually looking at not just Q of the whole matrix, but Q of a nested sequence of principal submatrices. And this turns out to be connected to other topics associated with the inverse eigenvalue problem of a graph. Okay, some acknowledgements are in order as I close my presentation. Some of the work the work I described in this lecture involved a number of projects, and I can't thank all the people individually, but I can certainly say that some of the work here was with my postdoc, my current PIMS postdoc, Ahmed Mojahali. There was work mentioned in the discrete math research group here at the University of Regina. There was a Banff International Research Station focus group that I referred to, an Ames Squared research group that I made mention of, and then there's 2 subgroups working currently associated with the American Institute of Mathematics research community on zero forcing and IEPG that I mentioned here in passing. And again, I appreciate the opportunity to present my lecture. I acknowledge the fact that it's a wonderful opportunity for me to be invited to this conference and speak, and I appreciate all the help and the assistance along the way. As I close, here are my some of the references associated with this lecture, and I'll take any questions you may have. Thank you.
Professor Bapat, sir. Professor Prasad, will you please take over?
Yeah, I have noticed that maybe because of network problem or some issues, he is not here. You just to find out if there is any question from audience, Raksha.
Audience, are there any questions?
Yeah,
to
I
explore
have
if there
one.
is. Sukanta has a question.
Yeah. Son, very nice talk. That monotonicity, I mean, the monotone result that you showed, right, related to the subgraph and that inequality, monotone result, right, related to subgraph. There you said, okay, that is going to increase, but has there been some kind of characterization where it will actually remain the same?
Good question. I mean, I would say there's been no like characterization of when it will be the same, but
Yeah, I thought I will ask the question so that you can maybe in future.
yeah, the problem is the way the theorem is used is you're going to use the strong spectral property based on a subgraph and a graph, and what happens is you can preserve the number of original eigenvalues, but our theorem says that you have to necessarily add new simple eigenvalues that are completely distinct from the original set of eigenvalues. So what that technically implies is that, you know, the use of the theorem technically implies that there will always be a gap in some regard. But that's just the way our proof went. It certainly doesn't say that you might be able to do something a little bit differently in the construction to show that there is, an equation and instead of a strict gap. But the way our theorem, the way we prove that result is that we have to actually add new simple eigenvalues, which of course increases the little q. So at the moment, we don't have a characterization where you can actually hope for equality per se, but
it is interesting.
You could, you could probably work something out. But
it is very interesting.
Yeah, no, but it's a great question. Thank you, Sukanta.
Okay, yeah, thanks.
Any other questions? Professor Prasad, would you like to?
Yeah, sure. Let me control. Yeah, these two are the lectures that I like to watch and just keep listening again and again and make something to get in. And I really enjoyed, and I'll get back to you people. And if there is no other questions, let us thank the speakers, all the speakers, and wind up this session.
Very good talk. Excellent talk.
So thank you, Professor. Thank you, Professor Jain. Thank you, Professor Andre and Professor Palat for the interesting session. I also thank Professor Bapat for chairing this session. So today we have come to an end of this program. Tomorrow, it's the last day of ICLAA. We'll meet at 9:15 IST. See you all tomorrow. Thank you.
Jain and Palat can start their day, and we will try to end our day today. Bye.
Thank you. It was a good talk.
Thank you. Bye.
Thank you. Take care.
Thank you, everyone. Okay. Close it now.